So good morning, so ladies and gentlemen. So I'm very happy to saw so many people join this webinar. At the beginning, I would like to our founding director, Professor Vinayak Dravid, give us the opening remarks for this GATAN Northwestern workshop. Let's welcome.
Thank you, Xiaobing. Good morning, good afternoon, good evening, everybody, wherever you are. We're very delighted to have you. This has been an amazing week at Northwestern. And normally one would have every excuse not to do this type of thing. It takes a lot of time, effort, energy. We have a new dean coming up. We have a new president, a new incoming chair of our department. However, at NUANCE and SHINE, we do things as they come and face them as they come. So we're very delighted to have this specific webinar and activity with GATAN. And it's a part of a larger program at Northwestern under SHINE umbrella. SHINE is Soft and Hybrid Nanotechnology Experimental Resource. It's an NSF Center of Excellence for Facility Infrastructure. And together with the University of Chicago and Argonne National Lab, we have this resource available for both university as well as industry in the region. It's led by the NUANCE Center, which you see in this slide, which is a comprehensive characterization facility, and 6 other facilities that complement together. They form the SHINE resource, the NSF Center. Next slide. So it's led by the NUANCE Center that goes back more than 20 years. NUANCE Center, think of it as a comprehensive characterization facilities. You can see there are 5 major ones. And today's event is organized under the auspices of both EPIC, which is our electron probe instrumentation. And in the past, some of the bio-cryo soft matter microscopy spun out of EPIC into a bio-cryo. KEC2 is our surface science, SPEED is our scanning probe. And NoFab is our fabrication facility, which is finding a lot of interesting application in microscopy, particularly in situ stages. But today's event is very specific to our GATAN friends with GATAN as well as NUANCE. And the next slide, I'd like to just acknowledge with gratitude number of folks and institutions involved. And there will be additional thank you at the end. We particularly want to highlight in the middle, GATAN has been a great partner. Now it's a part of EMETEC. A number of people that you listed here, and of course, many others associated with GATAN, we're very happy and grateful to collaborate with. On the left-hand side, it's mostly mine's the ceremonial role, but much of the work has been lifted by our admin staff, technical staff, and there are students who have been volunteers. And last but not the least, we must acknowledge with thanks and gratitude our invited speakers. And I see some recent graduates from Northwestern in the list, and I'm very delighted to have all of you. And I'm really looking forward to participating as things progress. As some of you may know, we have a reverse site visit of NSF Center today, so I'll be a little tied up. But otherwise, I hope you and the rest of the attendee can enjoy both the presentation that you see in the morning, and there will be tutorials in the afternoon. So it's a real treat, and I'm very delighted that we are offering that treat to a large crowd here. And again, I want to thank Xiaobing, Paul, and others who developed this particular program, and I've passed the baton back to Xiaobing. So thank you, and I will participate throughout the day.
Okay, Vinayak, thank you. So how can I say? I want to say thank you to Vinayak. In the past 30 years, we grow for a very, very small core, but now we are very big national Euro center. So thank you. Okay, so next I will introduce our first speaker, Dr. Lijun Wu from Brookhaven National Lab. So Dr. Lijun Wu is a very, very quiet, silent, super expert in TM field. I mean, when I was in Brookhaven, he has been working in Brookhaven for more than 27 years, around 27 years. So he developed many code. Maybe you saw that many simulation code, something like that. Actually, Lijun developed his own simulation code for both TM, STEM, CBET, and also the quantification of EELS and CBET, many code, and for the STEM too, using MATLAB. But maybe, yeah, he has many programs. So in the future, I believe if you have any question, you can talk to him. He's very nice. He's very kind to help others. So now I want to hand over to Dr. Lijun Wu. So Lijun, so you can begin. I don't want to occupy too much of your time.
Thank you, Xiaobin. Thank you to invite me to give the talk here. My talk today is mapping electromagnetic field, and let me use the valence electron distribution by 4D stem. The work was done with M.G. Han, Qinping, and Yimezu at the Brookhaven National Lab. The talk includes two parts. One is Lorentz 4D stem for magnetic field mapping. The second part is the valence electron distribution by multiple density function and 4D stem. The magnetic field can be usually is measured in Lorentz TM mode through phase retrieval. The phase shift in the Lorentz TM can be determined by the electrostatic potential and the Z component of the magnetic vector potential. And usually can be measured by the transport of intensity equation that is using two images with different defocus. Because it requires large defocus, so the spatial resolution is limited. Another way is use of axis electron holography based on wave interference. But this requires a wave reference from the vacuum near the interest area. This often limited its application. Also, it is difficult to decouple multiple scattering effects. This will make some artifacts in the magnetic field mapping. And another method is in the Lorentz STM mode, using differential phase contrast. This uses a segmented detector, and recently it's a 4D stem. This utilizes the pixelated detector. So we record the whole diffraction pattern at each scan point. The magnetic field is proportional to the diffraction angle in the diffraction plane. So once we can measure the diffraction angle, then we can determine the magnetic induction. It is in focus image, so it usually has a high resolution. And also it is possible to decouple multiple scattering effects. This is a typical setup for the Lorentz 4D stem. The probe scans over the sample, the interest area, and we record one diffraction pattern for each scan point, and recorded at the pixelated detector. And in the Lorentz 4D stem mode, the objective length is turned off, so the conversion angle is very small. It's almost parallel. And the disk shift can be formulated by classic particle physics or the quantum mechanism. And basically, it's proportional to the electric field and the magnetic field. As you can see here, typically for 1 Tesla magnetic field, the diffraction angle is only about the 24 micron radian, same as for the electric field. This is very small, so we need a very large camera lens. In this setup, I use the camera lens is about 4 meters. That's much larger than traditionally our electron diffraction. This is a small set of 4D stem patterns. It consists of 9 4D stem patterns from the 9 scan dots showed here. I don't know whether you can see it. So also here I show you the whole picture. This pattern is recorded in the CCD camera mounted above this pixelated detector. I marked the white square area. That's our recording area for the pixelated detector in the 4D stem. And the red square mark the area I showed here. So basically, we just record the central disk in the Lorentz 4D stem. As you can see here, this is one 40 stem pattern. There I've marked 3 centers. One is the reference center. So this center is the beam go through the vacuum without the diffraction. So it's called the reflection reference center. We can get it from the vacuum. And another center is the geometry center of the disk. This geometry disk is defined by the geometry. For example, if you draw a circle overlap with the edge of the disk, then you get the center. So this is a true disk center we want to measure. It's directly proportional to the magnetic field we want to measure. Traditionally, people also use a center of mass to simply measure the disk shift. Center mass is formulated by this formula. It's basically a weighted center. As you can see here, if the intensity distribution inside the disk is not uniform, then the center of mass will deviate from the geometry center by a few pixels. That will cause a large measurement error. To see the effect of multiple scattering to the intensity distribution and the disk shift measurement, we did both Brookhaven and the multi-slice simulation to see how they affect. The Brookhaven, the computation time increased sharply with the number of beams. So it's only good for the very small unit cell. But it's good also, but it is good easily to change the sample orientation and thickness. Multi-slice can handle very large supercells, so we can include the defects, grain boundary, sample geometry, but it is difficult to change the zone, the orientation. So they have both advantage and disadvantage. That's why we need to use both for the different situation. This 40 stem patterns are simulated by the Brookhaven simulation. Here, inside the probe, the thickness is uniform. But then we see how the intensity distribution change with the thickness and the orientation. As you see, if it's at the zone axis, the intensity distribution is center symmetric. So the center of mass is the same as the geometry center. But if we slightly tilt the sample away, just a fraction of a degree, then the intensity distribution change, and the intensity distribution change also change with the thickness. And if you have a bending, it also change significantly. So strong multiple scattering will change the intensity distribution, so change the center of mass. That will cause the large measurement error in the disk position measurement. However, we found that based on the simulation, we found that as long as the thickness inside the probe is uniform, then the disk position, the geometry center actually will not change, no matter your orientation or the thickness. So this gives us opportunity to remove the multiple scattering effect by developing procedure that can accurately measure the disk movement while just measure the geometry center. So we can handle the significant intensity variation. To do that, they have several ways. The most what people do is to convert the disk to the spot, so we can get rid of the intensity distribution inside the disk. People also use the Sobiel field, the cross correlation method. Here I will introduce the circular Hall transform and the pick position refinement. The circular Hall transform can convert a circle to a spot. The spot position is at the center of the circle based on this simple formula. Jianmin and Ren Liang, they used these methods to measure the position of diffraction disk for the strand map. Here I use a different approach. We first define the kernel. I call it the CHD kernel. The kernel consists of a single circle inside, or it's annular. Then we use this circle as the kernel and do the convolution. With using this convolution, we can convert this circle to a disk. This is showing in the logarithm scale, and this is in linear scale. This is a refinement. As you can see here, the converted peak is very sharp. This is 3D view. So after convert the disk to the circle based on the Sorbio filter and then the circular hole transform, then we get the peak. To measure this peak position accurately, we use chi-square and use 2D elliptical Gaussian and Lorentz function to do this. In comparison, other one they use the one-dimensional refinement. I think we find that directly using two-dimensional function is easy to do, and also we get a more accurate result. Here I show you, as you see here, the intensity distribution in the disk is not uniform. So the center of mass actually deviated to the disk center by 4 pixels. But using our approach, we can get a very sharp peak if the CHD kernel, inside that the kernel, the circle radius is same as the disk. Then the accuracy we can reach about go to the 0.03 pixel. Of course, if the kernel size you see different or larger or smaller, then the peak getting broadened and it slightly reduce the accuracy. So we need usually we will find the good kernel based on the experiment data. Here I show you a more complicated case. I see how the disk shape and the signal noise change for affect the disk position measurement. Because the disk may be distorted due to alignment or the distortion of the aperture, and the signal noise, we always need to deal with that. So first, to see how the effect of the shape. So I patch this circle go to an elliptical. If we still use a circle kernel, then the spots of CHD spots will have a different diffuse the shape, and then the measurement is not good. However, if we choose an elliptical kernel, then we can get a very sharp peak, and the accuracy is more is better than 0.1 pixel. This is the plot for the measurement error against eccentricity. As you can see, if I use a fixed circle kernel, the error increases with the eccentricity. But if I use the elliptical kernel, then the accuracy is within the 0.1 pixel. We also test the signal noise ratio. This is a very, I added a Gaussian noise to the image, and even for this very noisy image, we still can get the CHD peak and get a reasonable measurement resolution, measurement error. As you see here, if I use a small size Sorbio filter, this is a curve, is the measurement error against the signal to noise ratio. I also test for because in the experiment pattern, the edge of the disk may be blurred due to the diffuse scattering. So I convoluted the original image with a Gaussian function. And so the measurement error will slightly increase in this case. And here I add all these effects together. I add the shape effect. Also, I blurred the edge and add the signal noise. As you see here, our approach, you still get a very good Sorbio filter ring and the CHT spots. Although it's diffused, it's broadened, but the accuracy is still, I measured, is 0.06 pixel. That's pretty good. In the experiment, for the same experiments, when we do for the permanent square magnetic, we found at the edge, the disk actually is not a completed disk. You see the intensity intrude go to the upside. So it's if I do the Sobiel filter, then I basically get two rings. One is completed ring that's corresponding to the main disk. Then I see another up that's corresponding to the intensity intrusion or extension. So to find the origin of this this shape change, we did the multiple slice simulation because we need a very large supercell to include these effects. Brockwave is too large for the Brockwave, so we use the multi-slice. Well, based on the experiment condition, we need a very large supercell. This is a 512 by 512 unit cell. Consists of the supercell consists of this 512. It's up, but the supercell actually is the size is 182 nanometer, and the sampling we need the 64 million pixels. So it includes millions atoms. We modified the multi-slice simulation code based on so for this large supercell, because when we go for a wedge sample, the transmission function actually will change with the probe depth. So we dynamically upgrade the transmission function for this kind of multiple slice simulation. This is simulation result. This is the sharp edge. If we put the probe in the center of the edge, then this is the probe function at entry surface. This is the image at the exit surface. So yeah, the image we will see that the sample thickness is about 20 nanometer. As you see, half we have the sample. You see the dots, that's the atom, and half is the vacuum. The probe size, it doesn't change, almost no change, because the convergent angle is very small. And this is the diffraction pattern for the same pattern for this when probe is here. As you can see here, we see the main disk, but we also the intensity extend to the both side. And the Sobiel filter ring, we have a diffused ring. And then we go to the wedge sample. So the thickness will change linear in here with the position. Now we still see the main peak, original peak here, but the intensity will intrude go to the right side. That the thickness increase inside. This intrusion will increase when the inclined angle become larger, increase. So now I will talk about the experiment data. So we use the permanent square square, this material. It has a magnetic structure, the vortex structure like this. And this is one 40 stem pattern from the area inside this permanoid. The thickness is uniform in this case. So we see a disk, but we also, because of the multiple scattering, we see the intensity distribution is not uniform. So it's a center of mass deviate from the disk center. We used our approach using a kernel. We defined K2. Then we convert this disk to the spot, and we refine it. And you can see our refined circle actually match this disk very well. To compare with the other methods in the literature, mostly is the Sobiel filter cross correlation. That method uses the disk in the vacuum as the temporary image. our converged peak is much sharper than those methods and give more accurate results. More important, if we go to the edge that I showed before, this pattern is from this area, from the permaloy and this silicon nitride support. As is, I talked before, the intensity intruded to the this side. Then the other methods, we get a very complete peak shape if we use the Sobi filtered cross correlation. But with our method, we can separate these two peaks, these two rings, and get a very good refinement for the main peak. This is simulation. Not exactly match because the situation is different, but the major feature actually our simulation match the experimental very well. So this is a procedure for our approach. We first acquire the 4D stem pattern, then do the Sobi filter for all the for each pattern, and do the get the circular pattern and do the circular Hall transform to get the peak and do the refinement. Usually we will, for some local area, especially at the interface, we will do an iteration, look at the data, see possible artifacts, and change the filter, the kernel, see whether we can improve the accuracy. Once we do that, we get the diffraction angle map, and then we will correct the scan-induced disk shift, because when you scan a large area, actually your scan will introduce the beam tilt. That's also causing the disk shift. This can be corrected by record the same pattern from the vacuum. So we need to correct that, and we also need to correct the scan angle and the detector angle. Finally, we will get the magnetic induction map. I have developed a standard long windows program with the parallel code. So for a 200 by 200 40 stem data set, it only takes a few minutes to process all the data, get the map. So we can use this program for the in-situ experiments. So this is the what we have done for this. This is 2 micron terminal square. This is using the traditional center of mass methods to get the magnetic map. We can see a lot of abnormal points. That's basically because it's due to the center of mass deviate from the center a lot. Then we used our approach, as you see, we get a very clean the magnetic map. And also we need to be very careful because in some cases, for example, here we have a hump. The thickness will change in this area. This is inset from this area. And if we use the center of mass, we will get these artifacts. We see the up component, but we use our approach using if we with the same kernel, then we still see some artifacts, this component. So we need to define a local kernel, CHD kernel, then we can suppress these artifacts. This is my second part. I will briefly talk about the mapping valence electron distribution by 40 stem. The valence electron distribution is important because usually when the atom forms crystal, it's mostly the valence electron change. The core electron will stay the same, and so the valence electron is affected the property of the material. Traditionally, the valence electron distribution was measured by the single crystal X-ray diffraction and also combination of single crystal X-ray and the convergent beam electron diffraction. But these methods require large single crystal. So because now we have 40 stem, we can use very small probe to scan the in unicell with the sub-angstrom resolution. So we think it's probably good to use 40 step for the charge distribution. Actually, people already did this using the center of mass method, but I will talk about its limitation. In this slide, I show, so we first calculate all the electron density for a single atom, and the valence. And then we can convert this electron density to the X-ray scattering. And using more best formula, we can convert it to the electron scattering. As you can see here, the valence electron mostly is contribute to the low scattering angle parts, both in the X-ray and the electron scattering. But electron scattering is more sensitive to that. And the atom position will mostly affect the high order reflection. So if we have the 40 stand data, we can use the low order part for the valence electron distribution and high order for the atomic position and the Borel factor. We similarly, we will use multiple density function to model the valence electron distribution. In X-ray field, people already used this to refine the charge distribution. But for electron diffraction, there's no commercial software including this multiple function, including valence or this kind of thing. So we developed the program our own. We built the program with the multiple function, and we can do the Bloch wave calculation for the seabed pattern and also for 40 stem pattern. Now, this is a setup for the 40 stem for charge distribution. In this case, we have a very large conversion angle, so to get the sub-angstrom resolution. Then the scan area is very small. It's probably only a few unit cell. And this is calculated 40 stem pattern. It's actually this consists of 19 by 19 40 stem pattern. As you see, each circle actually is a 40 stem pattern is here. And the crystal actually I have the multiple density function model. So it's include the bounding and a spherical charge distribution. As you can see here, the 40 stem pattern, the symmetry is consistent with the crystal symmetry. This as is I copied from the international tab. It's a symmetry. So at the titanium side, you have a fourfold symmetry, but the auction side, you only have a twofold symmetry. This I show you the difference map for the valence. As you see, this I use insulated atomic model. This model IAM is simply use the neutral atom put together. There's no any bonding, no charge transform. Usually in the commercial software, when you do the simulation, they use this kind of model. But here I use multiple function. As here I use junction is 2+. And the titanium is 3+, oxygen is 1.67 minus. And also I put the non-spherical optical for the titanium 3D electron. So this is the plane 001 plane at the titanium 2 plane. So you can clearly see the oxygen is charged. It's not uniform. It's not spherical, as you see, it's elongation. And also titanium, you can see it's a fourfold. This is bound difference map. But if we calculate total electron density and the projection along 001, then you see the difference is not too much. So the this feature, optical feature, is reduced significantly because by the core electron, because the valence electron is only a fraction of the total electron. And it may be it's different from the you will not just get the limited information. You will not get the 3D charge distribution information. And the center of mass method by the 40 stand, what we get actually is the projected total density convoluted with the probe function. So the orbital feature in the crystal is further washed out by this probe the probe function. This is what convoluted with the probe, or the total electron density. And so if we just simply use center of mass, this is what we get. So the information is very limited. And also it's only applied for the very thin sample. This is only 0.78 nanometer, less than 1 nanometer. If we go thicker, for example, even just go 10 nanometer, for the center of mass methods get the charge distribution is now it's totally different. It's wrong. That's because of the multiple scattering. The linear parts, the center of mass related to the charge is only, as you can see here, is within 3 nanometers. So we thought we should fully utilize the 40 stem pattern. That's the whole information. Here we want to see the sensitivity of the 40 stem pattern to charge distribution. As you can see here, it's very sensitive. As you see, this 40 stem pattern using the IAM model, and also this is independent ion model. So I will use the ion to form the crystal, and this is multiple density function model. We can clearly see twofold symmetry. And this is the probe is at the oxygen side. But if we put the strontium side, we also see significant difference with the different model. And the sensitivity here, I show you this is calculated at the 20 nanometer, before it's 10 nanometer. The sensitivity actually is increased with the thickness, but the pattern getting more complicated. And as I said, we can use the high angle part to form the virtual high angle annular dark field image from the same 40 stem data set. Use this, we can measure the atom position, as you see here. This column corresponds in the strontium and the titanium oxide. We can, based on position, determine the atom position. We can also fit the intensity to determine the Debye factor. So with the same data set, we can get the atomic position, structure, and also the charge distribution. And what we propose is we can calculate all, based on the simulation multiple density function, we can calculate all the 40 stem pattern at a different site, and then we can compare with the experiment to do the refined. Finally, we will get the valence electron distribution. This is a comparison based on 40 stem of our proposed methods, multiple function 40 stem, compared with the COM, center of mass based 40 stem. We can use for the 6 sample, but center of mass only work for the very thin sample. And here we compare with the traditional quantitative Ribet pattern. And the advantage is we can have a huge data, the big data, because when you scan more scan points, you generate usually it's several gigabyte data for one experiment data. And we can use the high order for the atom, that's for the crystal structure. And this is a summary. So we develop methods to calculate the 40 stem pattern based on multiple density function and also mode slice simulation for the wedge sample. We developed new methods to accurate measure central disk shift for magnetic field mapping. And we also show the 4D stem pattern are sensitive not only to the charge transfer, but also spherical electron orbitals. This is all. Thank you.
Okay. Okay, Lijun. So we already have one question. So anonymous attendee asked that about zero loss energy filter, the 40 stem may be better for thicker samples. Also can remove the intensity variation for 6 samples. Can you comment on this?
Energy filter, I don't think you can remove the intensity variation because that's, as you can see here, in this simulation actually is similar, equivalent to the energy filter. So it's all it's elastic scattering calculation. You cannot remove that. But the energy filter is good. Actually, you can remove you can improve the sharpness of the disk, the edge, because that edge, the blur of the edge blur basically is due to the diffuse scattering. That could be removed by the energy filter. So it could improve the measurement accuracy.
Okay. Okay, I would like to add one sentence, 2 sentences maybe. For energy filter 40 stem, I don't think you can, it's very tricky because we can do the energy filter 40 stem here because we have a new generation GIF system and also very fast detector. So I think this afternoon, GATAN, when they do the demo, they will particularly introduce this new capability, the energy filter 40 stem. I think that's one. Okay, so we have another. Yeah, we have another 2 questions. So actually from the same attendant. So one question is, can you discriminate the E field and the B field respectively?
If they exist in the same sample, it's I don't think you can distinguish. But usually it's not. Usually the sample you only have electric field or the magnetic field. But I don't know what his E field mean because
electric field
atom itself have electrostatic potential. That you have the electric field. That's the atom itself. We can distinguish from that if he means that. I don't know.
Another question is
the electrostatic potential.
Yeah. Okay. Another question he asked is, do the diffraction beams also shift? And also, how much does it move relative to the central disk?
Diffraction disk, yes, it will move. Yeah, for the wedge sample. Yeah. It should be. I tried one, but I did not pay attention whether it's proportional to the reflection angle or not. It probably was proportional to the reflection angle for the disk for diffraction disk movement.
Okay. Okay. Thank you, Lijun. I think our time is short. We can stop here. Thank you, Lijun, for the nice talk. Lijun is very nice. He, how can I say, not only understand, he understands the fundamental things behind the 40 stem. So I believe if you have a further question, you can reach to him directly. And he has many code. He already helped many people to quantification TM. So yeah, thank you very much, Lijun.
Thank you, Xiaobin.
Okay, now let's move on is Liam from GATAN. So he will introduce us the new capability from GATAN. And yeah, let's welcome him. Liam.
Right. Okay. Good. Okay. So yes. So thanks again for the nice introduction. And thanks also for the opportunity to present at the webinar. It's always fun to talk about, electron microscopy and EELS at these kind of events. So my presentation is titled Following in situ reduction dynamics with multimodal EELS and 4D spectrum imaging. So essentially EELS spectrum imaging, 4D STEM spectrum imaging on the same things. So before we kind of get into the details, we might ask ourselves, why do we want to capture data continuously? So essentially, why might we want to do in situ experiment? And this is a pretty nice example of just some energy filtered imaging that was done on a complex molybdenum sulfur molecular material. And we've got some energy filtered images here on the left, energy filtered images here on the right. And this was an in-situ heating experiment done with a counting camera with a K2. If we kind of look at what happens in between, you can see that there's some really, really rich kind of changes in this particle as we kind of heat this particle up. So if we only got data at the beginning of the experiment and at the end of the experiment, we would be missing all of this kind of rich information that happens as part of that reaction. So it's quite important when we're doing in situ that we want to watch things happen like as they happen, and it gives you more information and allows you to kind of have a more complete story about what we're looking at. Okay, so that's kind of the rationale behind an in situ experiment. And so how does GATAN fit into that kind of ecosystem of in situ? So in the distant past, when I think I was a PhD student, I think we kind of were more in this space. We have some heating and cooling holders, but that in recent years has expanded greatly. So we now have in situ capability really across the board. So we can do imaging techniques, so TEM, STEM, tomography, diffraction, so we can do 4D STEM, strain mapping, associated processing techniques with diffraction and 4D STEM. Analytical is really the group of techniques that we associate with energy filters or EDS spectrometers, so electron energy loss spectroscopy, energy filtered TEM, EDS, then we have holders, and then the kind of the glue or kind of for this all is digital micrograph. So the software that we use to kind of drive the hardware, acquire the data, do data analysis, kind of fancy holder integration and scripting. So this is the ecosystem. I'm going to kind of switch gears now and talk about the hardware that we're using at Northwestern and at GATAN to do the experiments that kind of form the basis of this presentation. So what is that system? So it is a GIF continuum K3 IS with Stellar. So that's our current generation electron energy loss spectrometer with 2 counting detectors, and it's an in situ flavor of that system. What's really cool about the Continuum IS is it kind of crosses all of the stuff in this ecosystem. So all of these techniques can be kind of achieved or you have access to with the energy filter. So we can do imaging, energy filtered imaging, and we can do the spectroscopy techniques. Okay, so what is the Continuum K3 with Stellar? So essentially, it's an energy filter, our Continuum system, and it has 2 electron counting detectors. So we have the K3, which is a retractable detector, and then there's a terminal camera, which is a Stellar. And the reason that Stellar is added is essentially to add low KV support in the counting regime. So this was originally like kind of a modification to our K3 Continuum system. So K3 gives us the highest performance large format electron counting system for EELS. So it has a really great point spread function. Large pixel format means that we have a large number of pixels. So it's really great for FTEM and filtered imaging and counted EELS. So by adding a hybrid pixel detector, so the Stellar camera, what we're doing is we're kind of pushing down the supported KV range right down to like much lower energy. So the K3, the energy support there in terms of the beam energy on the microscope is 80 to 300 kV, whereas the hybrid pixels, the stellar detector, comes down to 30 kV and it goes up to 200 kV. So there's some overlap in between. And yeah, so basically, yeah, it gives you much extended energy range there of the microscope. Okay, so the two detectors, right? They're quite different. So now we're going to talk a little bit about the detectors. So first detector is the thresholding hybrid pixel, like direct detector. So that is the stellar camera. How does the sensor here work? Okay, so we have something where we essentially have a very thick silicon diode. On top of the diode is an ohmic contact. That's bonded to an ASIC chip, and this is where the readout happens here. So, okay, so what's the important thing here is the direct detector in terms of hybrid pixel detector has to deal with all of the electrons within a single pixel. So those pixels, as a consequence, are pretty large. So they tend to be kind of this type of technology. You'll have kind of on the lower end, you'll have pixels that are like 55 microns, up to maybe 150 microns in size. And then this silicon layer here, where we catch the kind of primary electrons, is very thick. So it's 300 microns here. So essentially the primary electrons come into this silicon diode and completely deposit all their energy into this region. And then we're reading out with these really large pixels. So what are the kind of pros and cons of the hybrid pixel detector, so the stellar camera? So advantages. We have near zero read noise, so it's really great for high-speed EELS or multiple pass frame summing. So that's good for imaging, good for spectrum imaging. Broad range of input count rates. So that essentially means that we have a really big dynamic range. So these are really good for like low loss EELS, also really good for diffraction because we have a huge dynamic range on this kind of detector. They have a very sharp point spread at low kV, so we have really good kind of energy resolution and imaging performance at low beam energies. Limitations, they're physically large, okay? So those pixels we saw are, you know, multiple tens of microns. So we have large pixels, we have to fit that camera into the same space on the energy filter. So kind of the knock-on effect there is we have a small pixel count. So we don't have as many pixels as on a K3, for example. Counts are summed in the camera. And then a consequence of the larger pixels and the thicker sensor is that we have a poorer point spread function at high kV. So these guys, in terms of EELS and diffraction, are going to work much better at low kV. So it's actually a really nice pairing for the K3 detector, which is a different type of technology, which I'm going to talk about in the next slides after some application examples. So this is actually kind of a nice example of some data that we got from a sample that was provided by Northwestern, so the Dravid group. So a nice example of something that you can do with the stellar detector that we didn't previously do with the K3. So we're looking at molydisulfide coated silicon nanoparticles. These damage primarily with knock-on damage because it's 2D material. So we have this TMDC layer that's bonded onto the silicon nanoparticle. Stellar allows us to do counting EELS at beam energies that we didn't have access to for counting EELS. So we're able to do this at 60 kV. Dual EELS spectrum imaging on these materials that we couldn't previously look at. So this is ADF image on the left-hand side, and then some EELS, dual EELS derived chemical maps that are kind of from this guy here. So you can see silicon L map in red, and sulfur L, molybdenum M in green and blue, respectively. Okay, so that's kind of where I want to end with the intro to the hybrid pixel. So what's the other camera? So we have what's called a counting monolithic direct detector, or a MAPS detector, and that's what the K3 is. So very different to the hybrid pixels. So we have an active detector that's very thin, and the electron beam actually just passes through this detector. So it's a transmission sensor, and we're reading that actively in the pixels on this sensor. So these pixels are much smaller, so 5 microns instead of like multiple tens of microns. And so what's kind of the advantages of this type of technology? So again, we're electron counting. So we have near zero readout noise, and we can do things like multiple pass frame summing, which we'll come on to later. Has a really big advantage of having this centroiding kind of methodology, which extends our DQE, so our effective resolution, and reduces our alias noise. These detectors, we're actually counting every electron like at the pixel level, so we have access to every electron strike. These detectors have very, very sharp point spread function at high KV, and they're large format, so we have more pixels. Okay, so what are the limitations? We have nonlinear behavior at high count rates, so we need to make sure that we don't have too high a dose rate or beam intensity on the sensor. And then these guys have a poorer point spread at lower KV. So you can see this is actually the opposite to the hybrid pixel. So pairing the hybrid pixel with the MAPS camera is actually really good, because then you have two detectors on the same system, the same energy filter, that have quite different characteristics. So you get the best of both worlds. Just a quick example of an energy loss spectrum that's acquired from a K3. So this is done at 200 kV, 900 milli-EV per channel. So that's our lowest spectrometer energy dispersion. So it gives us a really big energy field of view. So 3.1 keV energy range to 3,100 EV. Because we have a super sharp point spread function, we're actually essentially point spread, with dispersion limited in our energy resolution when we run like this on this microscope. So this was done in our F200 in Pleasanton. We're using a cold FEG. Our energy spread of the cold FEG is about 0.4 EV on our system. What we end up with is an energy resolution of 0.9 EV. So you get really nice sharp ionization edges. You can see quite nice fine structural features, but over this huge energy range. So this is a single spectrum. And we can zoom into these areas here. So you can see we have like really nice kind of fidelity in our transition metal L edges here. So I think lanthanum, iron, probably cobalt here. So these are really sharp. You can see how sharp these white lines are, like single channel. Then what's kind of cool is if we go out to higher energy loss, so that the strontium L edge, even at high energy loss in the same spectrum, you have really nice kind of good quality out here, because we have the counting, it's a sensitive detector. So we have high quality, big energy range, high fidelity. So it's a really nice detector to work with. So yeah, so kind of in summary, this is really giving us best in class performance, because we have these two like very advanced counting detectors on the same kind of spectrometer base. And yeah, as I said, this is the system that we're using in Pleasanton for all of the work, and the same system that's on the ARM 300 at Northwestern. So how does this factor into the in situ ecosystem that I was talking about earlier? So what did we add that's new very recently? So we've recently added in Digital Micrograph 3.6, the newest version, well, soon to be released version of our software. We've added in situ support for, in situ spectrum imaging support. So we can do in situ 4D STEM, in situ spectrum imaging for EELS, in situ spectrum imaging for EDS. And that's kind of where I'm going to go with the experimental examples that I want to talk about. Why is spectrum imaging with a counting detector particularly advantageous? Okay, so we're doing our spectrum imaging with zero read noise, okay? With a traditional detector, so a fiber coupled system, we have readout noise on those cameras. So what the typical workflow that we would do with the traditional detector is that we would maximize the signal per camera read to get above the noise floor. And then we want to minimize the number of detector reads so we don't keep adding readout noise together. With the counting detector, we don't have readout noise, so we can always go as fast as we can. This minimizes any delays. We have like high time resolution. We can do faster drift correction. Combine, we spread out our dose. Loads of advantages, but in kind of the realm of in situ, this is particularly advantageous because it allows us to oversample in the temporal domain as we're acquiring our data. So that's kind of useful because we might not know ahead of time the time resolution or the in situ stimulus resolution that we need. So we can oversample so that we make sure that we're in kind of the right kind of resolution space for in the time domain. And then we're able to rebin as needed, like when we analyze the data after the fact. So we can sum as many in situ counted frames as we like after the fact with no penalty. So this makes these kind of experiments like much more straightforward with these kind of detectors, because you can always go at the maximum speed, which is very much beneficial for an in situ experiment, and then you can just sum afterwards. Okay, so how does the workflow kind of look in the software? So this is a screenshot of the STEM spectrum imaging technique in digital micrograph, if anyone hasn't seen it before. So you have a bunch of palettes, and we typically work from the top to the bottom. So you can see we have in situ here is already enabled. So we just switch on in situ mode. And that means that we just get kind of a time series of data. And then the workflow, if anyone is familiar with spectrum imaging and digital micrograph, is at that point pretty similar. So we set up a scanned image. So we choose our field of view, focus, and rotation. We do something related to the spectrum image timing. So we choose how long our spectrum image pixels want to be dwelling for, say, for a better sentence. We also need to choose the signal. Okay, so we've got three options. If we have kind of EELS, EDS, and seabed, you've got these buttons up here. So what we're showing here is an example just for 4D STEM. So seabed is selected there. We can choose whether we want to do drift correction or such things. Then we will set up the detector. So in this case, we're doing camera things because it's a 4D STEM experiment. Then we can set up some in situ stimuli conditions. So in this case, it's a heating experiment. And then just press record. So once you're done with that, there's a record button here. Record just means that we're going to get a time series of spectrum images. So it's as simple as that. So what's particularly nice in digital micrograph is that, you know, if we have an EELS spectrometer, an EDS spectrometer, we're able to do all three of these things. Okay, so we can do not just one kind of spectrum image modality, we can do multimodal experiments. So digital micrograph is essentially multimodal at its core. So the spectrum image engine supports all of these kind of different signals. So EDS, EELS, diffraction, cathodoluminescence, if someone had a CL detector, and kind of all on the same software platform, all on the same hardware. So yeah, as we've just seen, it all lives within the STEM spectrum image technique. And so we just enter here, choose whether we want to do like a 2D array, multi-point line scan, etc. Choose our signals. I just seen this on the previous slide. So with a GIF, this is like particularly powerful because we're able to get all of these different data types in the same experimental session from the same specimen region. So that's really powerful because you can do really nice correlative analysis, and we can get spectrum images that are drift corrected to each other, same pixel resolution, same pixel density. So we can be really confident that we're actually getting data from the same exact region of our sample, which is really good. So, okay, so this is something that we've done really recently. I just wanted to record an example of an experiment in practice. So this is an in situ heating experiment. So this is a pretty easy multimodal experiment because we're doing dual EELS and EDS together. So it's pretty easy to get EDS with EELS or EDS with seabed because it doesn't disrupt us doing anything, because exactly the same electron optical configuration, we just have our EDS detector inserted, and then we're getting EDF data as well. So I'm getting 3 spectrum images here live. Basically, you can see it's a time series, and this is from this iron oxide powder. I am grabbing a picker region from the EELS and the EDF, and then I'm just tidying up the workspace a little bit. So you can see that is essentially the sum of all of the EELS and EDF spectra that we're looking at there from the whole region. There is like live drift correction that's happening, and we're ramping the temperature up from, I think, room temperature up to 900 Celsius. So in the manner of progress, we're just making it go a lot faster. And what's nice, if you look at the ADF survey image here, you see morphological changes that are happening in the ADF image. And then we can kind of pair that with chemical changes that I'm showing in the EELS. So what I'm doing here is like a live quantification using 2 references. One is for iron 2, one is for iron 3, and this pie chart is just showing us the quantification. So essentially the iron should be in a majority 3+ oxidation state at the beginning of this experiment. And as we heat it in vacuum, it reduces, so we get kind of an increasing percentage of iron 2 as the temperature goes up. And then right at the end, it does something pretty dramatic, and we'll see. I won't give it away in about a second. We have some real spontaneous change right at the end in the morphology, and the chemistry completely changes. So I think here we've probably formed some metal. Okay, so that's an example, that a nice kind of show and tell of how the in situ works in the software with a live example. So first, multimodal experiment, EELS and EDS. So EELS and EDS, okay, so they are both essentially analytical signals, so both giving us information about chemistry, kind of what we have, or like the bonding, if we kind of look at the EELS experiment. So these guys are pretty cool to have together. One kind of supports the other. What would be really nice is to have EELS and seabed, okay? So EELS and seabed are quite different. So they're giving us like really like different information, but like getting EELS and seabed data at the same time is more challenging, okay? So we're using the same detector when we get EELS data as we get 40 STEM data. We're just changing the electron optics in the filter. So we're projecting a diffraction pattern onto the camera instead of an EELS spectrum, okay? So the long and short is we can't do those things simultaneously. They have to be done in a serial manner. Okay, so we're gonna go down that kind of path. So how do we do energy filtered 4D STEM and EELS together as part of the same experiment? So again, this is another example where I'm heating oxide powder. So instead of iron oxide, now this is copper 2 oxide. So the first example here is just some commercial oxide. Here's some copper oxide that was just drop cast onto a lacy carbon support film. And I did dual EELS and energy filtered 4D STEM on this material over a temperature range of like room temperature up to 600 Celsius and pretty coarse step sizes. Okay, so 50 Celsius or 100 Celsius. The reason being that the first time I tried this experiment, it was a manual affair. So it's basically easy to get this data in the software, right? There's a button in digital micrograph over here, which we'll see later in the live demo, which just says FTEM and EELS. And all we need to do to go and get a EELS data set is basically to have EELS button pressed here, capture our data, then we can just press FTEM, and then we're in a setup to get 4D STEM. So we just alternate between EELS and FTEM. So to do it manually is pretty straightforward. But to do a manual in situ experiment is quite like time intensive, because obviously you need to get like multiple spectrum images, and we're getting 4D STEM and EELS together. Okay, so it's time intensive, but why do we do it? So there's just lots of really great information if we spend the time to kind of do the experiment this way. So in the HADAF imaging, you can see that there are quite dramatic changes in the morphology of this particle that I've heated up. So room temperature on the left, and there's somewhere in the middle, 350 Celsius in the middle here, and then high temperature on the right. Okay, so we have real big changes here in this particle through this heating range. So let's first look at the EELS. So again, I used concurrent standards to map out the oxidation states of copper. So I have good references for copper 2, copper 1, copper 0. And we generated RGB composites for each temperature step. So blue is copper 2, red is copper 1, green is copper 0. So as we expect, we reduce this guy in vacuum as we heat it up to elevated temperatures. So we see a trend from majority 2+ at the beginning of the experiment to kind of a mixture in the middle of some 1+ oxidation state, and then metal and 1+ copper at the end. So if we pull out some EELS spectra from these regions that are shown, just to show that we kind of believe what we see, we do see LNS fingerprints that are very characteristic of these oxidation states. So super sharp white lines here for the 2+, then a decreasing kind of L3 intensity for the 1+, and then almost like no white lines at all for the 0, which is what we'd expect from the chemical information here. Okay, so this is only part of the story. Okay, so the EELS tells us a lot, but it doesn't tell us everything. Now, if we do 4D STEM, we can have really nice kind of energy filtered diffraction patterns from the exact same regions at the exact same temperatures. So if we look at the 4D STEM, we can kind of confirm or kind of do some phase confirmation by seabed. So we get like structures here in our diffraction that are consistent with the structures that we expect from the EELS. So to have both of those pieces of information, it kind of really kind of gives you a very strong case for the conclusion that we want to draw here. So I talked about some limitations earlier. So the main limitation here, we have loads and loads of data, but the manual acquisition is time intensive. So our temperature resolution isn't great. So what we saw here in this manual experiment is that we have like basically a massive change between like one of the increments. So 350 Celsius to 400 Celsius, big change. So how do we improve that whilst making the experiment practical? So the approach is to adopt kind of a custom method where we can do something with scripting. Okay, so what's the workflow here? So we can fully automate our experiment. Basically, we can go around this loop. So reason we need to do this, essentially, this is an irreversible reaction. We need to get the data as we go. We can't come back and get it afterwards. So we have to do it this way. So make a script. The script can control the holder, so it sets the temperature. We can do some drift correction after we set the temperature, which makes sense. Acquire an EELS and an EDS spectrum image, save and close that data, change the filter mode to F10, acquire a filtered seabed, and then reacquire the EDS signal because we can get the EDS for free. That means that we can add the two EDS data sets together at the end and double the signal. Change the filter mode back to EELS, iterate the temperature, and then just basically go round and round this loop, okay? How does that compare to the manual experiment? Okay, so when I did this manually, with the time that I had, essentially, it was only really practical to do temperature steps of 50 Celsius. I only made 10 measurements. So I only get 20 spectrum images in total, but I was at the microscope for more than 6 hours. Doing this with a script, I was able to get a temperature resolution of 2 Celsius. So I'm increasing my number of points that I measured from 10 to like over 200. Way more spectrum images, so 880 spectrum images, because we have 2 EDS spectrum images, EELS and 4D STEM. And then I'm at the microscope for less than an hour. So in terms of like user time efficiency, this is really high. And then this ran overnight, just autonomously, and we got the data in the morning. So it really increases the temperature resolution of this particular experiment like drastically. and gives us like a massive increase in like user productivity, because we can just leave the microscope to run the experiment autonomously while we go and do something else, or we can run the microscope at night when no one's using the microscope anyway. So it's good for tool efficiency, it's good for user efficiency. Okay, so what data did we get with this version of the experiment? So this was same batch of powder as we heated before, but the results look a bit different. Okay, so we have like this grid or this matrix of data. So we have the ADF, it's the top row, this MSM data, so that's maximum spot maps. So they are kind of essentially like pseudo orientation maps. So that's something that is derived from the 4D STEM data. If anyone's interested in that, I can point you to a paper that my colleague Ben Miller wrote. So he wrote a script to produce these kind of maps. We also have lots of interesting EELS data. So copper fine structure mapping, we can do oxygen fine structure mapping, and we'll see some other stuff on the other slide. So going from left to right, you can see that essentially these are like summed ranges of temperature. So we have like 40 Celsius, like chunks in temperature, even though like the actual step size was 2 Celsius. So this summing works really well because this was done with the K3. So as I said, you don't pay any penalty to do the summing like after the fact. So that's why we did this. So, okay, so what does the result show? So again, we have morphological changes that we see in the ADF, orientation changes that we see in the 4D STEM, and then we see the same trend in the chemical analysis. So the blue here is corresponding to copper 2, green is copper 0, and red is copper 1. So we reduce the copper as we kind of go up to elevated temperatures. What's particularly interesting with this sample here is this one actually has a lot more going on than the previous particle that we looked at. So we had bigger energy range in the spectrum here, so we're able to do some like basically we can see zirconium. We have higher energy resolution, so we could do oxygen like LNES fingerprinting, and interesting here is we have things in this particle that we really didn't expect to be there. So we've got a zirconium rich particle here. If we pull out like even more information, so we did EDS as well. Okay, so we've got titanium, iron. So there's like elements here that we didn't expect to be here. So this is where the EDS really comes beneficial for this experiment, because if we only had the EELS signal here, we'd potentially be concerned that these would be artifacts, but we're able to get like a nice titanium L map or a zirconium map, and then we can get a different map from our EDS signal, and just to validate the EELS data essentially, or vice versa. So we have a titanium K map that looks pretty close to our titanium L map. We have iron L in the EELS, we have iron K in our EDS. And yeah, guys, this is a one-shot experiment, so it's really useful to have like all of this like information. So we have EELS over a very, very wide energy loss range. So we can do fine structure mapping, we can map lots of different elements. We also have the EDF, we also have the 4D STEM. So the original data set, actually, I only looked at the copper and I didn't have like things like the silicon. It was much, much harder to analyze the data in the original experiment because I just had not such a good bird's eye view of the chemical changes and the structural changes that were happening. So I think that's pretty much everything that I wanted to talk about in terms of the experiment. So just to summarize, if we're doing an in-situ experiment, it's really critical to capture all of the data as we go at high time resolution to give a full story of material transformations from start to finish. If we just take data before and after, it's often insufficient to draw accurate conclusions. Electron counting detectors are really, really well optimized for in-situ experiments because they are inherently high speed and high sensitivity. And we have this zero readout noise. So it really is really beneficial to allow us to oversample in the temporal domain and then sum our data afterwards. And then digital micrograph and continuum IS, really powerful tools for multimodal analysis mainly because we can do everything in the same experiment. So being able to just get data from the same region at the same time makes your life significantly easier when we're running the experiments. So yeah, just want to thank everyone for listening, and that's the end of my presentation.
Hi, Liam. Thank you very much. We have several questions here. So the first one is truly amazing to able to see the multiple signal occurring. What brand of EDS detector can be used? Oxford, MTech, Bruker, Thermo Fisher, and how well is the integration of the EDS detectors?
So yeah, so that's quite, yeah, that's it depends on the age of the system. So going forward, I think we only support we'll support Joel and the Elite T, so the GATAN, like the Amatec detectors, the EDAX detectors. So it'll be EDAX and Joel for like new installs in the future. But anything that we historically have supported in the past will basically continue to be supported for existing installs. So thermo systems are supported. It kind of depends on the detector and it depends on the software. So there are some, essentially there are like some thermo systems are supported, like some Oxford systems are supported. Is there a specific question? Yeah, it might be better to take that offline if there's a specific question about specific hardware. But in terms of like performance, the EDS systems are usually always like much faster than the EELS. So they will be supported up to like the maximum frame rate that the EDS detector will run at in the software, quite comfortably. Does that answer the question? Yeah.
The second one is regarding, your K3 camera is a low dose camera. So when you are asking, is there any possible damage for a K3 camera in 40 STEM? Because, for a diffraction, you have a very strong central beam and a diffraction beam.
Yeah, so that's a really good question. So actually 40 STEM is not that high a brightness technique compared to EELS or selected area diffraction, because you have like the zero disk, but it's spread over multiple pixels. So usually it's okay. One thing that really helps when you're doing 4D STEM with the energy filter that we'll show you later in the live demo is that we're able to use, there's an electrostatic shutter in the spectrometer, and it allows you to attenuate the beam like significantly. So the shutter can go down to 100 nanoseconds. So pretty much, because the shutter is so fast, it gives you the ability, you can run the microscope in almost any condition, like with regard to diffraction and EELS, and you have enough attenuation in that shutter that you can always attenuate enough that the camera is going to be in a safe operating regime. And yeah, so you really don't usually have to worry about damage of the camera.
Okay. So I have additional one question. Is for the K3 camera, you can use both in the counting mode and linear mode, correct?
Yes.
Also in in-situ mode.
So essentially in-situ isn't really a distinct like camera mode. It's more like how the data is being recorded or saved. So when we're doing an in-situ experiment, essentially we're keeping all of the camera data as a time series. And so the camera is just, we're throwing frames through the data pipeline, and we're saving them all, and then we have access to all of them. So the linear and the counting modes are actually distinct different ways that the sensor will behave. And we generally always run in counting mode. So the linear mode has like slightly like a higher signal that it will take, but the counting mode is such better quality in terms of like the noise performance and the DQE that it really like it's the performance of the counting is so good compared to linear that we almost never use linear for anything currently.
Okay, Liam, during time limitation, so we will finish here. Thank you very much for your talk.
Great.
Okay.
I will stop my.
Yeah. So, I mean, now we will have a 5 minutes break. So we will come back on 10:35. So before we go, I want to say that we saw that, I mean, I think many audiences are coming from Asia. So it's a late night. So they ask us about recording video. So we can provide a recording video on our NUANCE Center YouTube. I already sent a link in your chat, you can see. And the second one is, I believe that some audience may have some questions regarding the data acquisition and the post-processing for EELS and for STEM and for many GATAN related problems. So I also provide a link. So it's a live, it's a live interaction link. You can put your question, and our admin team will collect your questions, and afternoon, GATAN technical team will show you answer your questions. And okay, and also in the second session, my colleague Paul will chair. So please remember to come back 5 minutes later. We will begin 10:35. Thank you very much.
All right. Welcome back, everybody. I hope you had although short, a good break. My name is Paul Smeets, and just as my colleague Xiaobing, I work in the EPIC facility at the NUANCE Center, where I manage our focused ion beam systems and our dual ARM 300F TEM. So it's my pleasure next to introduce the next speaker, who is Dr. Jianguo Wen. He's a material scientist and deputy group leader of the Electron and X-ray Microscopy group in the Center for Nanoscale Materials, or short CNM, at Argonne National Laboratory. His research is focused on development of an application of aberration-corrected TEM to solve material problems in battery materials, catalysts, photovoltaic materials, and quantum materials, amongst others. And he will be talking to us today about three-dimensional electron diffraction for structural analysis of advanced materials. So, Jianguo, we look very much forward to your presentation.
Yeah, thank you, Paul. So I will reduce the dimension from 4D into 3D. So talking about the 3D electron diffraction for the structural analysis for advanced materials. First, I would like to acknowledge our team, especially you can see the TM is done by those two guys, Nei and Yunin. And also we work closely with the battery group in Tao Cheng and Claire Amin. And recently also working with the people who synthesize materials, Shou Chen and the professor from Northwestern. And also Tao helped us to write a lot of scripts and also the data processing, and also a lot of help from Martin too. And finally, obviously, we got a lot of help from the theoretical modeling, Maria Chan, for our data analysis, and also AI machine learning. So we also would like to acknowledge our funding source. So as you know, the big challenge when we start to work in this field, see how are we going to sort of leverage electron microscopy, the huge data generated from electron microscopy. And there was so many sort of possible way to go. But one of the direction we're trying to think about, say, are we able to have an easy way to have the structure determination? Because this one traditionally is done by the X-ray, but we know the physical principle between the X-ray diffraction and electron diffraction, they are very similar. So they should be able to use electron to do the similar job. So, so one way, what we're thinking, say, hey, can we use 3D electron diffraction combined with the AI to have the material discovery. So I will give you the short introduction, and then I will try to show you 3 examples to use those 3D diffraction for those material problem, and then finally give you the summary. So we know this structure determination is primarily done by X-ray diffraction, and there are 2 sort of big category. One is the single crystal or the powder X-ray diffraction. In the single crystal case, typically you need sort of like 5 by 5 by 5 micron, that kind of single crystal size in order to get accurate sort of structure determination. That means when you grown material, you have to grow reasonable big material in order to do the job. And another thing is when you do the X-ray, you typically suffer from the X-ray peak bordering when the size is small, and also the peak sometimes they overlap, and especially at lower angle degrees. And also if you have multiple phases and those phases coexisting in the powder, then they will give you the trouble. It's very difficult to know which peak is coming from which phase. But the electron diffraction, compared to that one, we got several advantages and disadvantages. Especially the advantage is because the electron beam and sample, they have a strong interaction. So they give us 3 order of magnitude sort of higher intensity interaction compared to the X-ray. And because of that, we only need a very small amount of the material to do the electron diffraction. And not only that, because a strong interaction means you can sort of work with the light elements very nicely. And also the electron beam can allow us to focus in a very small probe size. Right now, we know we can easily achieve like sub-angstrom, just say 1 angstrom. And we also can do the sort of EDS and EELS, those kind of compositional analysis. But then the disadvantage of the electron beam is because it's so strong interaction, so you need a very thin sample, and also especially when you do the structure determination, and you need to certify this kinematic scattering. But well, the TEM case, you often suffer from this multiple scattering, which is dynamic scattering. And so we have to sort of overcome the issue in order to get this structure determination work. So to do this job, so that's sort of right here, basically right now the electron beam still suffer this sort of multiple scattering. To overcome this kind of problem, people tried many methods, and then especially the way they say is try to avoid this kind of the diffraction pattern coming from the major zone axis, away from the zone axis. And then they use all those kind of different names, sort of like say automatic diffraction tomography, or single crystal electron diffraction, or currently right now, gradually people moving sort of to this continuous rotation electron diffraction. So I will explain in the following slides. The reason to do that is basically when you do the electron diffraction before, they use step by step. Basically, you have the electron beam, the micron beam here on a sample, and then you gradually do the step by step. And so by doing so, then you acquire at each step, you acquire diffraction pattern, and then you try to measure the intensity and reconstructing from those data. But then you can see there is a lot of angle, the information is missing. And so the people later say, okay, can we try the precision? So basically rocking the beam in such a way, in this precision way, and then they can get more sort of like a cone shape, and then they will get more sort of data. And so by combining A and B, so they got this kind of the technique, and then basically you can rotate your sample continuously no, at a sort of an increase in step size, but also meanwhile, then they do kind of precision. But the precision is very small. Typically, it's only a very small angle, sort of rocking the beam. So recently, people more popular to use this so-called continuous rotation method. Basically, the detector will keep on open, and then they now you sort of continue to rotate your sample, and then try to get all the diffraction from all the angles, so you will not miss any sort of the diffraction from those angles. So using this idea, so basically we also did this kind of experiment at our center. So we use a tomography holder, and so basically we tilt the sample from -45 to +45. We can tilt high angle, but typically what we find out that's good enough. And then use those data so we can sort of do the 3D reconstruction to get this diffraction pattern. From those diffraction pattern, then we can sort of try to solve the structure. Okay, so this is an example. You can see that in the real space, when you try to tilt, this is already sort of close to the eccentric height. It's the movement is very minimum. You can see this one is within this 100 nanometer. We're using a selective area electron diffraction. On the right side, we can see this is the diffraction pattern sort of we acquired. And so currently we're using two approaches. One is using selective area aperture, but we also use the nano beam sort of electron diffraction, basically the beam coming from the top instead of using the aperture to select from the bottom. The good advantage of this nano beam electron diffraction is right now we are trying to control the beam because the sample is going to move, so we can easily trace this kind of moment with the angle, so we can adjust our sort of beam to follow this the particle movement, and then so in future, so we can do so-called continuous rotation diffraction, and also do the mapping. So that's the sort of ongoing project. As I mentioned, so using this diffraction, as you can see, this is the reconstructed sort of the 3D diffraction. You can see this one is from the lithium-ion battery. It's a standard sample, and you can see this very high good crystallinity, and also showed this sort of major zoom axis from the 001 to sort of 100 to other zoom axis. You can virtually sort of tilt the sample to any angle you want. Virtually, you don't have to physically sort of tilt to there. So using those kind of data, and we can do two major things. One is to determine the unit cell of the material. And this one is already very useful. So later we're going to show a lot of examples of this. Another thing is, after we determine the structure, and then we will be able to export each diffraction spot's the intensity, what we call the HKL list. Basically, that will give you the sort of like each diffraction spots, and then they will allow you to figure out the structure factor, and then finally using the software to resolve this kind of structure. So this is the sort of the approach we use to do the structure determination using 3D electron diffraction. And what we tried first is to for the very simple material, like say silicon. So you can see this is the 3D diffraction pattern coming from sort of silicon from the three major zoom axes, 110, 001, and 111. But here on the left side are the sort of the conventional two-dimensional selective area electron diffraction pattern. And you can see that they are different. The reason is because the two-dimensional sort of conventional selective area electron diffraction, it's an intersection of the reciprocal lattice by ionosphere. So but the three-dimensional, it's a projection of all those kind of diffraction pattern along your view direction. So this is a projection. This is simulated 3D diffraction pattern, and you can see they are sort of different. But this one definitely match with the sort of the experimental data we have. Okay, so using those kind of structure, the kind of information, so we did sort of reconstruction and also did a structure determination, and then what the structure we figure out is pretty much with this one nicely. You can see the lattice pyramid and also sort of the atomic location, and from the CRED and from the X-ray, they match very sort of nicely, which give us good confidence. But then when we start to move to the complex compound like this one, the lithium cobalt O2, and then you can see this is also 3 major zone axes, because this one is close to the hexagonal lattice. So you have 001 and 210 and 100, 3 major zone axes. And so those are also the simulated diffraction pattern, as I mentioned to you. And especially you can see there are 2 things you need to pay attention here. One is you can see in the 2-dimensional kind of diffraction pattern, and this one is much bigger than this one. And not only this, they rotate the symmetry, rotate 30 degrees. This is something we have to pay attention when we do the experiment. Okay, so using those data, we did the same thing for the structure determination. So what we find out is, you can see here, the structure, the A, B, C, the match with the data pretty nicely. But the biggest problem is, you can see this heavy atom, transition metal, cobalt here, match with this one from the X-ray nicely. And also the oxygen octahedra here also match with this one, but the lithium here is missing. For some reason, we are unable to determine the lithium atom at all. So what do we think is, this is because right now we are using the conventional CETA camera provided by the GATAN, but recently we acquired a sort of pixel array detector. I think this one, especially like the Stellar and MPAD, they should be able to do a better job. The reason is because when we acquired the image, sometimes we use the beam stopper to block the transmitted beam. But even when we are not using this one, because this one is saturated our detector, so we reduce the sort of the acquisition time dramatically in order to not allow this one to saturate, and that makes sort of like a lot of sort of a big signal to noise at this area. And then by doing so, then those kind of light element scattering was not very nicely recorded. So in future, we're definitely going to try use those kind of sort of direct electron detection detector to improve the quality. So now I'm going to show you the sort of 3 examples to use that kind of 3D diffraction technique in slow the material science problem. And the number one we tried is sort of the battery material is a lithium-rich layered sort of oxides. So what happened is, as you can see here, the lithium cobalt oxides, they give the capacity of this one. And then you can almost double this one by adding this kind of so-called lithium 213. So basically, this chemical compound is complex, but you can write into conventional layered structure plus sort of like 10% of the 213. By adding this 213, and then you can get a huge sort of increase in sort of double the capacity, which is a big deal. But the problem is during the cycling, this one suffered a voltage fade. Basically, this one, when we doing the cycling, then we cannot know which one voltage should we cut off? And then that's a big sort of problem. If we cannot resolve this issue, and this material cannot be used at all. So because of that, so we spend a lot of efforts to understand the voltage fade issue in this kind of material. So give a little bit introduction and structure. Because this layered structure is sort of like rock cell structure, and you can see this lithium oxygen transition metal. And transition metal layer here is fully occupied by the hexagonal lattice. And you can see, if you view along this direction, you should see the 3 dots as shown here. So basically all 3 dots, and this is a layer structure. But then when you have the lithium 2 manganese 1 and O3, and then you can see this sort of the lithium manganese 6 flower. And when you view along this direction, you see the manganese, and lithium, which in the head-up image, you show a sort of like a dimmer sort of spot, which means here there is existence of 2 and 3 phases. So, and this is the sort of the starting material. And when we do the cycling, the diffraction, conventional diffraction show that, and you got the mixture of the 2, 1, 3, those 2 sort of row, plus the 1, 1, 2, the layer structure. But while the cycling, you can see the 2, 1, 3 become weaker, but still there. And then you can increase the sort of the 1, 2, 3, 1 to 4. It's a spinel structure. Even in the first cycle, they already showed that. Okay, so now we're trying to use the 3D electron diffraction. And this is the pristine. This is the pristine sample. You can see this is the sort of layer structure plus 2, 1, 3. As you can see, those kind of 2 sort of a continuous line. This contribution comes from 2, 1, 3. And then when we after 1 cycle, and we can see there was extra sort of diffraction spots come out from here. Okay, the most interesting thing is when we did the 40 cycle, unlike the conventional two-dimensional sort of selected area electron diffraction, now we see more information, especially when you come to 001, it looks like still perfect. But when you go to side, you can see they show a lot of like arc kind of structure. And that is because of the lattice is severely sort of distorted. And then then we use those 3D electron diffraction, then we can sort of figure out, especially in some direction, you can see here, there is no sort of the tilt lattice distortion, but then at a certain orientation, they show the distortion. So we don't have to physically tilt to there, but using the 3D electron diffraction, we are unable to identify the lattice distortion happening in the which plane and which direction, how severe they are, and also at which sort of cycle state. So combined with the sort of the high resolution TEM imaging of those kind of lattice distortion, and also 3D electron diffraction, and definitely we also use other technique like EELS mapping, etc. And then we are able to answer the questions to study the sort of the structure distortion caused by those kind of phase. Then finally, sort of we figure out the mechanism is because you have the coexistence of those 2 phases, but these 2 phases, they show different sort of the electrochemical property, which means the different cycle voltage. So then some material, they already pull lithium out, but here the lithium is not out, and then they cause huge kind of the strain between those 2 materials, and because of that, then they cause this transition metal and oxygen release, and that caused the sort of the fade. Because of that, so this paper is published in Nature last year. Now I'm going to show you the second example. So especially this is for very important for the so-called material discovery, because people synthesize now, they're able to sort of using different way to synthesize a lot of material. Like in this case, they can easily synthesize like 100 types of new material. And then, so in order for them to do the structure determination, currently, they have to first make this material very big. So then the second thing is, in order for the X-ray to do the single crystal X-ray diffraction, the second thing is they have to make the phase single phase, and both, because of this both job is very challenging for them to develop this sort of new material discovery. So recently we worked with them together and to speed up the sort of material discovery using using 3D electron diffraction. So the idea here is to just give you a very simple idea what they are doing. Basically, they have two different layer kind of material, but then they melt them into the flux, and then they are able to let them to insert in the atomic level, then they form the kind of total new material. So this new approach, they sort of published this paper in the Nature and also in the Nature Synthesize recently in the last 1 year. So here I'm going to show you some example. We use the 3D electron diffraction to do the structure determination for their new material. So this is the one example we showed, say, this is the yttrium-4 iron germanium-8, and you can see, we can use the EDS composition to figure out what is the composition there to begin with. And then we can use 3D to figure out structure unit. This is the X-ray they did because we want to make sure whether this is the true or not. But in addition to that, we can see a lot of red spots we reviewed from 3D electron diffraction, and which is not shown by the X-ray. And then using the conventional high resolution electron diffraction and selected area electron diffraction, we find out this one did show very strong sort of modulated structure. And so this one is, which is not reviewed by the sort of the X-ray diffraction. So what I'm saying is we are able to resolve structure like what they did, but also we can find something new which they did not see in the conventional X-ray diffraction. So in this system, in the same kind of the material, we've also, because we are able to do the electron sort of EDS, so we find out there was another material called 688 material, and then in this one, then so this one basically they did not find by X-ray, but we are able to use our 3D electron diffraction. We find that this is another sort of new material because this is so small crystal, and so they don't need a big crystal in order to answer those questions. So this is another example I just showed you. This is another system. Is basically is a strontium 2 manganese O2. This is a one layer structure, but then also they coupled with this copper sulfide, but this is not sulfide, but using another sort of material, not copper oxide, but this one using different sort of material. And then, so you can see those kind of new material is completely new, and we are able to use the 3D electron diffraction and EDS and combine it with the aberration correction and selected area electron diffraction to figure out, for example, exactly the composition. For example, here you can see almost no manganese, and here there is manganese, and the sort of the modulation, the structure, all show the different structure. So basically we use this one when demonstrate. We can sort of, in some cases, we can do better job than X-ray diffraction, especially for the fine structure. Okay, now I'm going to move to another sort of direction, what we call sample tilt, especially atomic resolution imaging for beam sensitive material. So this idea basically is already proposed in 2018, the science paper. Basically, what they're saying is you have to because reduced electron beam when you do the sort of sample tilt for those kind of material. The way to do it is basically when they see such kind of diffraction pattern, they should be able to figure out where the zoom axis is, and then they will tilt without sort of the opening electron beam, and then final tilt sample to zoom axis, and then they will do the sort of corresponding electron high resolution imaging. And so that's what they demonstrate in this paper. Okay, so what we did is, so we use 3D electron diffraction. So here, what we want to see is we use examples to study this, how the ice grown from the supercooled water. So we know conventional ice, they show this hexagonal sort of ice, but the supercooled water is like this. Basically, they will remain in the sort of in the liquid until like -40°C. And so especially in the Chicago area, in the winter time, if you leave a bottle of this water in the car, you can see this is sort of cold, but it's still water, liquid sort of state. And if you shake the bottle just gently, then you will see this one sort of so you will grow like this one. They will quickly sort of convert it from water into ice. So surprisingly, when we studied this material, we find out this one shows 8 branches instead of 6 branches. So basically using this 3D electron diffraction, as I show here, we are able to get atomic resolution image of those kind of material. So you can see this is sort of this is basically hydrogen. We don't see it. This is the only oxygen lattice of this material. So we are able to see this one clearly. Not only that, we find out this material, as I see here, as 8 branches, and then we can find a lot of twinning structure. And so using the 3D electron diffraction, the reason for that is because because there were several branches, and some branches like here, this dimmer one, they are the sort of the basal plane is inclined. So physically, we are unable to tilt this one in order to see it. But we are able to use the 3D electron diffraction. For example, we use the right column, we select this area and do the 3D diffraction. Then we are able to figure out the twinning relationship between those two. So all those results is matched with this Nature paper reported. Basically, when you have a super cold water, then they form a lot of stacking force, a lot of twinning, and then they will there will be sort of much energy favorable compared to you have using the sort of conventional sort of hexagonal ice growth near the melting temperature. So so this is the sort of the 3 sort of example I showed you. But right now, in continue to make this work move forward, we're planning to sort of introduce a lot of AI machine learning. One of the big challenges, we want to make this one automatically sort of for the sample. Basically, we acquired a sort of electron diffraction and then make this one automatically sort of the tilt. Currently, we are using sort of the manual way, we got it with 3D electron diffraction, and then we will manually sort of see, what is where is the zoom axis? So using this one, we're manually able to tilt the sort of to it. But obviously this one can be done by the sort of AI machine learning. And after we do that job, then here to do the atomic resolution image, currently a sort of advanced instrument should be, this one should be easy. And then from this side, using the 3D electron diffraction combined with the EELS, we can make this one also sort of automatic. You can see, use all those kind of information, we should be able to provide very quick and sort of response for the material discovery. So because this one right now, not only in the battery field, but in many fields, we have sort of tried to use an AI machine learning to search for new material, but they need electron they need a characterization method to provide a feedback what kind of material you synthesize. Okay, finally go to the summary. Basically, we demonstrate we're able to use 3D electron diffraction for structure determination. And we showed you 3 examples. And hopefully we can combine this AI machine learning in the future to sort of to do the sort of massive structure determination for this new material discovery. Yeah, thank you so much for your attention.
Thank you, Jianguo, for this great talk. There's a couple of questions in the chat. Maybe the first one I'd like to ask is how do you actually deal with the missing wedge, and does that give any problems in your reconstruction?
So for this one, this is a very good question. So we do not have so we're not doing the sort of the real space reconstruction. So we do basically if we tilt like 30 degree so plus minus 45 degree, the missing angle effect or the contribution to the diffraction sort of intensity is not huge like the when we do the real space reconstruction. Then you have sort of the missing wedge issue. But definitely tilt high angle will introduce another effect because you increase the sort of thickness. We find out a tilt to too high angle actually introduce more problem. So that's why we sort of keep it to the plus minus 45 degree instead of like plus minus 70 or higher for the imaging reconstruction. Yeah.
Thank you. And then another question is there a way to check that intensities are not affected by dynamical scattering effects?
That's we do not right now. The way to check it is right now because this method, the biggest problem is still suffer from this dynamic scattering. So the one thing to resolve this issue right now, we are trying to do several approaches right now. One is we sort of maybe we have to reduce the sort of the particle size even smaller. So because of that, then we have to, instead of using the selected area electron diffraction, basically you got a huge area, the electrons come in sort of from the vacuum, not from your sample. So you basically increase the sort of the background. So we have to use sort of smaller nano electron, nano beam sort of to, but then when you use small nano beam, the sample is going to move. And so that's why we need to use the program to trace the particle, and then we can use our nanobeam, follow the particle exactly, and then we can sort of reduce the signal to noise as how we do it in this nanobeam electron diffraction for this sort of reconstruction. So this is, and then the second sort of way we need to do is so far we're using the conventional CCD, but then definitely we need to use the like the GATAN Stellar, those kind of detector to sort of have much huge dynamic range, and then so we recording those kind of diffraction pattern, which allow us to absolutely determine the intensity. And so to answer that question is basically so far we're still trying to compare this one with the X-ray data to see whether because if the intensity measurement is not correct, then the structure, the refinement come out with the wrong sort of information. That is so far, this is the way we are doing right now. Yeah.
Thank you very much for that elaborate answer. Actually, in response, you tackled another question as well, because somebody asked if there are any changes in Z height and camera length during sample tails rotation. So for your selected area diffraction, that certainly is. And if you want to do nanobeam diffraction, indeed, then you would need to resort to like AI learning or to basically create a feedback loop to minimize these these type of artifacts. So
Yes.
thank you for that. Maybe one more question that I can ask as a follow-up, maybe a more practical question. So would it be possible to do continuous rotation tomography combined with precession to even further reduce dynamical scattering artifacts?
Yes, that is definitely, it is sort of. But what we find out from the theoretical part, we thought about that. What we find out is the continuous rotation sort of should be good enough for this one. But there is something we can do is because this is something right now we are using the sort of single tilt sort of tomography holder, but we would like to, because since we don't need a very high tilt angle, so we are thinking now using the conventional double tilt holder instead of the, because then even if we use plus minus 40 degree and single tilt and with a little bit beta tilt, the reason is if we can sort of ensure during the tilting, we're not cutting to the major zoom axis, all the diffraction pattern coming from the sort of away from zoom axis, and then that intensity sort of should satisfy more sort of kinematic scattering instead of using the precision. So that's another big issue. This is we learned from X-ray is when we tilt the sample, actually the intensity will sort of, we measure the intensity of the beam, but actually the transmitted beam intensity also change. So in future, when we use this sort of direct electron diffraction detector, we should be able to sort of change sort of multiple by the calibrate by the central beam in order to get the correct sort of the intensity scattering. Yeah.
Thank you very much for your answering the questions and your great talk. Thank you.
Thank you. Yeah.
All right, then it's my pleasure to introduce our next and final speaker for this morning session, which is Dr. Stephanie Ribet, who actually obtained her PhD last March here in the Material Science and Engineering Department at Northwestern University, working with Professor Vinayak Dravid. She's currently a postdoctoral researcher who works with Colin Ovis at the Lawrence Berkeley National Laboratory in Berkeley, California. And amongst others, last fall, she won the MRS Gold Graduate Student Award for her research on virtual detectors and beam modification for these STEM experiments. So we're very thrilled to hear her talk, which is titled Iterative Phase Contrast Techniques for Dose-Efficient Reconstructions in STEM. So Stephanie, the virtual floor is yours.
Thank you, Paul. Well, thank you very much for the introduction and the invitation. I am very excited to be here. Let me switch here. And I'm going to be talking about some work I did. I started here at the NUANCE Center during my PhD, and now I'm working on at Berkeley. And I've been working on sort of working on some code for these phase contrast techniques. And I'm very excited to be sharing this with you all today. So I'll start by kind of introducing the problem that we're trying to solve. So the problem that we want to solve is sort of this phase problem. So what we have in our STEM experiments, we have this complex probe, and it's going to interact with our sample, which has a complex transmission function. And our simplest understanding is we can have this exit wave like this. This is going to be a complex exit wave. And the problem is going to be right here. On our detectors, we're going to record the intensity of our exit waves, so we lose all this phase information, which is really important for understanding our samples. So anything we can do to get back this phase information is going to have a number of benefits, two which I'll highlight here, which is that we're going to be more dose efficient. So this is going to be good for beam sensitive materials. And you also have this linear contrast transfer function. So you can see heavy and light elements at the same time. So really the theme of my talk today is going to be how we can use 4D STEM to recover this sort of phase information and get back this information about our sample. And I'm going to be showing a number of examples. So yeah. And before I get started too much about talking about the techniques that I'm going to be explaining today, I just want to say that this work that I'm sharing I've been doing in collaboration with George Varnavides and Colin Opus, and I'm definitely very excited to be sharing this on behalf of all of us. And so we have been working on developing some tools for doing a bunch of different phase contrast reconstructions. And depending on what sorts of 4D STEM data you have, you're going to want to use a different technique. And there are a number of factors that can influence what your 4D STEM data looks like. So you're going to have a different probe size, and this is going to depend on your convergence angle, if you're diffraction limited, and also any aberrations that you might have in your probe. Some of them we may add on purpose. For example, defocus would be the most common. You're going to have some rotation between your real space and your reciprocal space. Any sort of you're going to record what you can with your detector. And then, of course, you're going to have any sorts of other artifacts in this 4D STEM data set, from experimental artifacts and dose limitations as well. So depending on what your 4D STEM data looks like, you might want to use a different phase reconstruction technique. And the techniques that I'm going to be talking about today are first differential phase contrast, which we discussed a little bit earlier this morning. Another technique, which is parallax, which you can use for recovering the phase of your sample. And then I'm going to be talking about a couple of different flavors of tychography. I'll say that all of this work that we've been doing for developing these different phase contrast techniques is part of a larger effort to develop these in Pi4D STEM. So this is an open source repository with freely available codes. And a lot of the examples I'm going to be showing today are actually part of our tutorial notebooks. And so we've been working on making these techniques available there. And before I explain too much about these different techniques, I want to take a step back for a second and explain maybe why we're doing this. A lot of these techniques have existed for a very long time and have certainly become more popular as people have done more 4D STEM and detectors have gotten better. But we really wanted to develop this code for a number of reasons. First, it's really helpful to have all these different approaches in the same place. One, for comparing, and also I hope to emphasize in the talk today that these techniques really flow together. So you might want to start with a DPC reconstruction before you move to tychography to solve for the sort of parameters that you'll need for you doing your tychography reconstruction. The second reason, of course, is going to be algorithm development. So thinking about what signals we can get, and then also thinking about how to make this faster or how to make this better for our computer memories, which are sort of maybe opposite. And then the last theme is really thinking about experimental data. So these ideas in theory and in simulation work really well, but experiments are much more challenging, and you have all kinds of different artifacts that you may have. So we're thinking about what regularization parameters you need and how you can really deal with experimental data and get back these phase contrast reconstructions. So I'm going to start with DPC and explain how this works. And to talk about DPC, the first thing you need to do is talk about center of mass. So for this example, I'm going to be using this data set from the Muller group at Cornell. This is the twisted bilayer of MOS2, and this is our dark field. What we're going to do is, well, I'll explain the theory first. So you start with your electron beam, and when it interacts with your sample potential, you're going to get its change in center of mass. And we can measure this, and we're measuring this for each position in our data set. So we get this sort of images that look like this. This is our center of mass X and our center of mass Y. To get a good reconstruction, we want to solve for our real space reciprocal space rotation. So we're going to rotate on reciprocal space our diffraction patterns, and we're also going to transpose, so flip our X and Y. And we're trying to minimize this function. So you can see here we have a minimum value around here, just past 25 degrees. And this is because our center of mass is going to be our gradient of our DPC, which is proportional to our phase. And we're going to assume that our potential should be conserved vector field. So what we want to do is find this sort of minimum point here. And now we can see our corrected center of mass images, and we have our X and we have our Y. So this is going to lead to a better DPC reconstruction. We have one more piece of information that we didn't solve for our rotation, which is this sort of 180-degree ambiguity. And we can solve for this by knowing that our sample should have a positive potential. So what we're going to do is take these center of mass corrected images. And as I mentioned, so 4D STEM captures this change in center of mass. The center of mass is going to be the gradient, and DPC is proportional to the phase of the sample. So we can use these center of mass corrected images to get this nice DPC phase reconstruction. And I'm going to use the same MOS2 twisted bilayer for a couple of different techniques. So we'll do a comparison at the end. But this is a brief simulation. This is graphene with a vacancy. In this particular example, you can see that DPC is going to be orders of magnitude better than dark field. These phase contrast techniques can really be much more efficient. And of course, it's going to depend on, this is a simulation, but your experimental parameters, your convergence angle, all kinds of other things. But I wanted to emphasize that these sorts of phase contrast techniques really can be more dose efficient. So now let's look at another example of DPC. So this is going to be some gold nanoparticle data that I was taking. So this is a dark field image here and DPC. And in both cases, we can see that we have these gold nanoparticles and we have solved for our rotation. It's about 12 or 13 degrees. And this is really nice for solving for the rotation, but we have one problem. We'd certainly expect to see a lot more features in this image. I'm using an aberration corrected microscope. And this leads to our first limitation of DPC, is that the aberrations in your probe are going to be imparted in this image. So this is a data set I took defocused on purpose for tychography, and you can see that DPC doesn't work well for this in focus data sets. We can overcome this limitation a little bit with another phase contrast technique based on real space, and this is going to be parallax. So what we're going to show here is a movie, and I will explain first. So if you take a virtual image from each pixel in your diffraction pattern, one thing you'll notice for defocus data is you're going to see these shifts of your real space image in the diffraction plane. So if I go here, my image might be shifted on one side, and then here it's shifted on the other side. So if I play this movie, you'll see we start in the center and these images are pretty well aligned. But as we go further away from the central point, we're having these larger and larger shifts of our image. So what we're going to do is do a cross correlation between all these different virtual images for each pixel and our diffraction pattern, and we get a vector field that looks like this. This is helpful for two reasons. First of all, we again solve for our rotation. We know how much these images are rotated to align to get the highest signal to noise image. And then the second advantage now is we've solved for our defocus. And this is a parameter that we're going to need for our tychography reconstructions later. And we can see that we have also good agreement in this data set between our DPC and parallax. So I'll show these phase reconstructions now. And this is our parallax corrected. And we can see that we have a higher signal to noise than any of these virtual images. We see more features in our gold nanoparticles in the carbon, which is good. And then we can apply a CTF correction, much like you would for TEM, to get the defocus rate. And you can see we have our phase shift correctly now here. So this is a really nice technique for increasing the signal to noise, getting a good phase contrast image. The limitation here is going to be that your resolution is based on your real size sampling. So in this case, the data set isn't high enough to be able to see lattice features in the gold nanoparticles, but we will see this when we get to tychography. So both parallax and DPC are really great phase contrast techniques. They're much computationally pretty quick. They're great for recovering the phase of your sample, and the limitation is going to be your real space step size. So now let's talk a little bit about tychography and sort of these iterative approaches for tychography. There's a number of different approaches for tychography. So what you're going to do is start with a guess for your sample and your probe. And then what you're going to do is simulate their interaction and compare this to your experimental diffraction patterns. And then you're going to update your probe and your guess, your probe and your sample, and you're going to do this for a number of cycles. And you're going to do this for all their probe positions in your 4D STEM data set. There are really a number of advantages to tychography. So first is you can get this sort of super resolution imaging effect, which we'll see, which is that your resolution can be set by your diffraction patterns instead of your real space sampling. And the second benefit is that you're going to be solving for your complex probe in addition to your complex object, so you can remove any sort of aberrations that you might have. And in fact, we might even add aberrations on purpose. So you can see here, if you have an in-focus probe, it's going to be focused to as fine a point as possible. And this is what you would want for a conventional image. However, if you defocus the probe, you have a much larger probe interacting with your sample here. You're going to have a shadow image of your sample in these diffraction patterns, and you can kind of recover your sample potential from this defocused data set. And the advantage of this is, in addition to your normal benefits for your phase contrast techniques of dose reduction, you also get dose fractionation. So when you take this data set, you want to have some overlap between your probes, but these are going to be much bigger probes. So you take these big steps in real space and you cover your sample area like this. So this is sort of going to be another advantage of tychography. Now, there's certainly some limitations as well. So you're solving for these two complex objects. You only have so many measurements. You're not guaranteed to converge. And especially if we start looking at experimental data sets, there's a lot of other challenges to sort of getting nice reconstructions of both your probe and your object. And this is also a much more computationally expensive and more complex sort of algorithm than we've discussed so far. So I'll demonstrate how this would work in practice. And we're going back to this MOS2 data set. So this is what our probe would look like. We know what our convergence angle is from taking the data, and we have a guess from our defocus from these previous methods. And then we're going to guess what our sample potential is. It's a weak phase object, so we're going to guess that our object phase is close to 0. We've solved for this rotation, remember, and we know our sampling in real space. So we can simulate where these probes are going to be, and all of these red positions are where we think we have a probe. And then we can simulate what happens when this probe interacts with this object phase. And we get our kind of data set looks like this. And we're going to compare this now to the experimental diffraction patterns, and we can see that this is not the same. But that's okay. We'll take this difference and use it to backpropagate and update. So we can see now we've updated our object and we've updated our probe. And we're doing this, remember, for each probe in our data set. One thing about our implementation in Pi40 STEM is we have this sort of parameter that you can tune that has a big impact on your reconstruction, which is the number of diffraction patterns that you're updating at once. So you can do anywhere from updating all your probes at once to updating fewer, going down to just updating one. And with the more probes, you have often a more stable reconstruction, and it goes faster at the cost of you need to have more space in your computer memory for this. So in this case, we're updating all of our probes at once because this is a pretty small data set, and we can see what happens as we update for multiple cycles. And I think I'm just doing 8 iterations here, and we can see now we have much better agreement between our reconstructed data and our experimental data. And so now we can do the comparison that we talked about before between all these different phase techniques. This is our dark field image, which is not nearly as good as all these different phase contrast reconstructions. We have DPC, we have parallax, and we have tychography. Tychography has the highest resolution, but in this case, is really not so different from these parallax or DPC. So this is a case where, because this data set was taken in close to in focus, perhaps maybe one of these DPC or parallax would be sufficient for kind of trying to answer the questions you wanted to with these phase contrast reconstructions. I'll show another example here, which is going to be with the gold nanoparticles. So we saw this before. This was our dark field in DPC, did not do well with the defocus data. The parallax did even better. We were starting to recover some features, but we're limited by our real space step side. And for this data set, which was taken with defocus tychography in mind, is sort of the best reconstruction where we can see these lattice planes in our gold nanoparticles, and we've recovered this only with tychography. So now the question might be, how do we take experimental data? What is the best way that we should do it? And I think the first answer will be simulations before you go to the microscope to help you figure out your parameters. And there's certainly a lot of things to think about, but here's sort of a few examples. So we're looking at a simulation here. These are going to be 2 carbon nanotubes, one inside the other. And we're seeing, how much do these 2 parameters matter, which are dose and overlap. So we'll start with overlap, and you can see what happens here. So we're going from left to right, where you have a lot of overlap between your adjacent probes, to the further to the right, where you have less overlap. And you can see in these algorithms that having a lot more overlap helps with these reconstruction. And this is because you're going to have more redundancy in your data set. And so this is going to help your reconstruction converge. So we have a better reconstruction over here and a worse one down here. So this is going to help you think about how to take this data, and might be a little bit different than more conventional imaging modes where you don't want to have this overlap. Another thing we could think about is dose. So although these are more dose efficient than a lot of other techniques, you're still going to need, sufficient electrons to be able to get atomic resolution imaging in these really high resolution experiments. So a lot of these really fine tychography experiments actually end up using a little bit more dose. So there's a trade-off depending on if you're really interested in low dose imaging. Tychography still has a lot of advantages and can be used for that, versus kind of thinking about what you're trying to get out of your experiment. I'll show some more kind of things to think about with experimental data. So this is a data set. We're looking at these samples with the Bediako group. This is a twisted bilayer of tantalum selenide, and it relaxes into these different domains of moire structures. And in order to recover anything from your tychography data, from this experimental data, you need to solve for a couple parameters. You need to know your real space pixel size, you need to know your reciprocal space pixel size, your rotation, and your defocus, the second 2, which we talked about a bit more. And although you record these parameters when you're on the microscope, they're not going to be exact. So you want to think about how you can solve for them even better. And we have a couple different algorithms and tools that we've implemented for better reconstructing these and solving for these parameters, but I'm actually going to talk about defocus because we've been talking about that in the presentation today. So I took this data set, and this was again intended for a data set from a sample like this that was intended again for super resolution imaging. So we have very few probes in real space and a lot in reciprocal space. So I used parallax to estimate the defocus, and it did a very poor job in terms of solving for the defocus. It guessed was about 200 angstroms. And this makes sense because parallax is going to be limited by your real space step side. And I knew that this was wrong. So what I did to follow up was to do this sort of Bayesian optimization to look at a larger space. So what we can do here is we start with a guess. So I started here at 200 and I gave it a larger parameter space. I expected a larger defocus. And it looked at a bunch of different observations and optimized the value to be closer to 670 angstroms here. And then when I ran the reconstruction with this new defocus value, I got a much better reconstruction, and we can see this even better in the FFTs of these. So you can see that we're actually able to resolve some of the atomic features when you're able to better solve for these parameters. So this is an example of defocus, but you can solve for multiple parameters at once. And this has been really helpful for trying to understand these real and reciprocal space calibrations that we need for tychography. So I'm going to talk about kind of two other flavors of tychography. So the first is going to be mixed state. So we can think about in our real experimental data, we're going to have some incoherence, and we're going to model this with some simulations. So we're going to simulate two 40-stem data sets. We're going to be looking at the strontium titanate sample here, and we're going to be having these different real space probes. And this is what the probes look like in reciprocal space. And after we do our 40-stem simulation, we're going to add these together in this fraction of 3/4 and 1/4. And then we're going to do our tychography reconstruction and see, can we get back a nice reconstruction of the sample? So we can start here. This is what our probe looks like with a single probe. And then this is our reconstruction. You can kind of see some atomic features, but this is not a very clean reconstruction. It's not very good. So we said, okay, let's do our simulation. We'll give it 2 probes and see if it can separate out these 2 different probes and then give us a cleaner reconstruction of the sample. So we'll see what that looks like here. This is I should have mentioned, a reciprocal space probe. Perhaps we are slightly closer here to this, but we have very little intensity. It's estimating here. The reconstruction is marginally less noisy, but certainly not much better. And so what we had to do to actually get a cleaner reconstruction was decrease our batch size. So remember, I said that if you have a higher batch, you might have the update might be more stable, but actually if you decrease your batch size, you're going to be able to reconstruct your probe better. So we can see here now this algorithm has separated out and let us solve for these 2 different probes. This is this here and this one here in their right fractions. And this is when we can actually get a nice reconstruction of our sample. We don't have all these different artifacts. So mixed state can be really helpful for dealing with some of these incoherent artifacts in your probe. The other thing we might want to deal with is sort of these thicker samples or multi-slice. So in these tychography algorithms, you have this sort of assumption that you're basically having a single interaction between your sample. And for thicker samples, this isn't going to be true. So there's a couple things to think about. One would be multiple scattering. And then also with a thicker sample, your probe is going to change as it propagates. So what we do is instead of just having one slice, what we're going to do have multiple slices of our sample, and we're going to propagate in between in our forward and backwards model. And this is going to help us for these sort of thicker samples. So we're going to do another simulation with strontium titanate here. And we can see first what happens with our single slice as a function of thickness. So even at this 13 nanometers, we're not able to get a very clean reconstruction here. And then as we go thicker, it gets worse and worse. We have these sort of donut wraparound phase artifacts. But if we switch to a multi-slice instead, we can get a much better reconstruction for all these different thicknesses. And we can resolve our atoms much more clearly and see what's going on. I'm now going to show an example of this from some experimental data. So we're collaborating with Dongxin Li at PNNL, and we're looking at this titanium dioxide grain boundaries. So you can say here we have these 2 grains, and in the middle here we have this grain boundary region, and all these bright spots are going to be our titania atoms. So the question is, can we see the oxygen and can we see better what's going on? So we start with our DPC, and we certainly can see more features. These are where we'd expect our oxygens to be, but this is a pretty thick sample, and we can't get a very clean picture of what's going on. It's sort of a similar story with the parallax. Again, we can get a much better reconstruction maybe, but we still have a lot of artifacts in this here. We can then do tychography, and tychography is going to be better than the DPC and the parallax. We can see these oxygens here, but there's still a lot of noise. And finally, our best reconstruction is when we actually switch to a multi-slice reconstruction. And we can see here, we can see all these different these oxygen atoms much more cleanly. And this is a pretty thick sample. We estimate it to be about 20 or 30 nanometers. And this is when you really want to be turning to your multi-slice tychography to reconstruct our samples. So I've showed a lot of material science examples. I want to show some bio examples as well, because you can use sort of the same sort of code for doing reconstructions of a different material system. So we've been working with Burke and the Stallberg group. This is at EPFL, and we're looking at apoferritin. And you can see here, this is going to be a sample. We have a hole in it here, which is actually quite helpful for aligning the data and solving for the different parameters. And this is our dark field. We do our DPC phase reconstruction here. We can see some features, but again, for a defocused data set, this will only take you so far. It gets a lot better with parallax. We can start to resolve these different apoferritin that we are expecting to see here. And we can solve for our defocus with this, and then use this for a tychography reconstruction, which is going to be our best reconstruction. And now we can see here that we're able to resolve these different features that we were hoping to see in this data set. So one last example of phase contrast, and I wanted to talk specifically about hybrid materials because this is NUANCE Center and we love our hybrid materials. So this is an example of a carbon nanotube here, and this is going to be these iodine atoms that are in here. They're heavier, and you can see them clearly in a dark field, but if you look at the phase contrast image here, you can see much more clearly what's going on. This is going to be a double-walled carbon nanotube and these sort of fullerenes inside. So this was an example from the literature where for this hybrid material, you wanted to see kind of both, and these phase contrast techniques were really helpful for being able to see your heavy and light elements at the same time. We like this data set a lot, so this is actually incorporated into one of our tutorials for Pi40 STEM, some data from this paper as well. And then another example of these sorts of hybrid materials would be these sorts of MOFs. So this is a DPC reconstruction of some MOFs, and you can see here, if we go to even higher resolution, you can see your heavy elements, so these chromium linkers with these benzene dicarboxylate heavy metal nodes and these soft linkers here. So this is the atomic structure. We're able to see both at the same time with these phase contrast techniques. And if you want to do these high resolution characterizations to understand the surface and what's going on better here, in this case, DPC lended itself really nicely to being able to do these reconstructions. So I've talked about a bunch of different phase contrast techniques. I've talked about DPC and parallax, and then a bunch of different flavors and applications of tychography. As I mentioned at the beginning, this is open source code and open source examples. So we have these tutorials online, and definitely something we're actively working on, still evolving. So thinking about, as we look at more experimental data, what sort of experimental and regularization parameters are the most important for thinking about convergence, and then also thinking about getting more 3D information. So combining these sorts of phase contrast techniques with some tilting, how can we recover that? So let me see. I think I have a little bit more time. I wanted to talk briefly, kind of change gears a little bit. I've talked a lot about software development for phase contrast technique, but I want to talk about hardware for phase contrast as well. In particular, beam modification. So the first application of beam modification that people may be using all the time is going to be actually these sorts of aberration correction. So in these big electron microscope, we have these magnetic lenses, and these are going to implicitly create these spherical aberrations. So this is what a spherically aberrated beam would look like, and it's not as focused to as fine a point as possible. And the introduction of these multipole lenses have led to this aberration correction. So we can go from this aberrated probe to this corrected probe. And we can look in the history of microscopy. We can see here light microscopy, and then introduction of electron microscopy gave us much higher resolution. And then finally, when we use this aberration corrector, we didn't need to go to higher voltages to get smaller wavelengths, and we can still get these really nice resolution. So this is the first way that people may be modifying the electron beam before the sample. And then there's other applications as well. So this is in TEM, we're trying to solve sort of the same phase contrast problem that I mentioned previously with 4D STEM. So this is what TEM would look like in focus. And the way that we often get more signal and can see better what's going on is to introduce some aberrations in the probe. So we can take our weakly scattering sample and we can get a better picture. So this is our defocused probe. Then we can do even better than this though. If we insert a phase plate into the probe, then now we can get an in-focus image where we can see more clearly what's going on without all these different aberrations. So this is in TEM. And in STEM, we kind of want to do the same thing, but there's definitely been fewer examples of this. So one example of this is going to be MIDI STEM. This is an example from Colin Ophis. And what he did is you incorporate the silicon nitride membrane in the probe forming aperture of your STEM, and you match the virtual detectors to this sort of phase plate. And you can see here, this works very nicely for these hybrid materials again. So with the gold nanoparticles and the DNA, we get much better transfer of information for the heavy and light elements by incorporating this sort of same phase plate beam modification idea. The challenge is this is kind of a difficult experiment. You have these thin silicon nitride membranes. They need to be cut to just the right thickness to get the phase shifts that you want. And they're not the most physically stable, and their phase shift isn't the most stable. And changing these sorts of apertures in the microscope is a day-long process. You have to vent the microscope, change them, and pump down. So this is not something we want to be doing routinely. So we're thinking about what are some tools we can use for modifying the electron beam and having this be a little bit more stable. So for that, we're working on kind of an electrostatic phase plate. So this is what the design of the electrostatic phase plate looks like. So we can have a two-terminal device, and in between the two-terminal device, we can create a potential. And as our electron beam is going to pass through this potential, it's going to be phase shifted. So we can change the phase of our beam. And you can imagine patterning out a series of apertures with this sort of two-terminal device, something like this. And to help kind of explain, you can see these would be the terminals, the red and the yellow, and each of these are going to have their own two-terminal device. And since they're independent, we can pattern this phase plate however we want to, so we can create something that looks like this with all sorts of different phases. We're also thinking about doing this for spherical aberration correction. So as a alternative to sort of the corrector that we talked about just earlier. And you can do this by having a linear ramping profile here. So you can do this for doing spherical aberration correction. So I'll show a quick example of spherical aberration correction, but I want to go back to this idea because this will connect more to the phase contrast that we've been talking about earlier. So imagine that you have a very spherically aberrated probe. This is your aberrated probe. It's pretty big in real space, and you have all these sort of colors show the different aberrations in reciprocal space. And we want to get to something that looks more like this. This is corrected. Our beam is much more concentrated in real space, and we have don't have these aberrations in reciprocal space. So what you do is, if you imagine this is the aberration function of your aberrated probe, we're going to fit our corrector to match this. So all these places that are 0 are where these crossbars are, and we're going to try and fit a linear profile to these aberrations and then apply the opposite phase shift to it. So this is what the residuals are. Our tolerance is pi/4, so we're never going more than pi/4 out of phase shift, and we can correct our aberrations. So this is sort of the impact on imaging. So imagine that you had a twisted bilayer of graphene with your aberrated probe. You can't see very much at all in the dark field in the DPC. You could try and just using a smaller convergence angle, so getting rid of these parasitic spherical aberrations, and you still just then don't really have the resolution to see much of what's going on in this sample. But with our corrector, now we can resolve in both DPC and dark field these atomic sites in our twisted bilayer. And then we can compare this to an ideal probe with the same convergence angle. And you can see one of the limitations of this corrector is going to be these crossbars. You're losing some efficiency of transfer. So this is something that we've been thinking a lot about. So with this idea in mind of this phase plate that's dynamic, that you can insert in your STEM, the question is, how can we use this for improving our tychography reconstructions? So there's been some discussion in the literature of sort of different probes and how they can do better for reconstruction. So this is an example from Philip Pels. You can see we're looking at a defocus probe, a probe with a Fresnel plate, and then a probe with random noise. And we're looking at, this is signal to noise at different frequencies for a human ribosome. And I want to point your attention to these solid curves here, and looking here in particular where you have put some phase structure, these two, in your probe, you're getting better transfer at lower spatial frequencies. So we're thinking about using a similar idea here for with our electrostatic phase plate. So for this example, I'm going to be looking at these tetracutinase molecules. These are these proteins connected with these nodes here. And I've done some work on these previously, and in order to be able to get good reconstructions, what we had to do was do sample preparation, so some staining and also some low voltage imaging, and then some post-processing to be able to get enough contrast and signal to noise in these images. So we proposed instead, maybe tychography could be really useful. So we can see what our tychography reconstructions look like. These are going to be very low dose reconstructions. This is the protective potential, and then we're going to be looking at different convergence angles. And with the smaller convergence angle, you get this low frequency information, and the larger convergence angle, you get this high frequency information. And sort of similar to the last example I showed in these simulations, now you can get these nice reconstructions where you see both the high and low spatial frequencies at the same time in this material with the same dose using this phase plate. So these sorts of phase plate can be really helpful for these phase contrast techniques as well. So in summary, I've talked a lot more about sort of different tools, software approaches for these phase contrast reconstructions, and a little bit more also about phase plates as well. And I have a number of acknowledgements. Specifically, I would like to acknowledge Colin and George and Steve for a lot of this work on phase contrast at LBL, and of course, Professor Dravid and Roberto and Kelly, who I worked with at NUANCE and Northwestern. And then we have a lot of collaborators as well. We're working on this. So I'd be happy to take any questions. I think I still have some time.
Thank you very much, Stephanie, for this this great talk. Yes, we have a number of questions in the chat. So one question is, well, actually, a comment that the parallax method that you showed is very very enlightening to the person that asked the question. So what does the parallax corrected image represent? Is that bright field image or direct phase of the object?
Yeah, so it's going to be more like a bright field image. Let me see, I can go faster, I think. If you go here. So well, maybe actually I'll go here to the slide. Sorry, the movie is going to play again. Okay, so when we do a parallax corrected image, this is going to be a lot more like your contrast from your bright field. Basically, we're getting a higher signal to noise bright field. So another name for this that you might have heard is tilt corrected bright field, basically. So we're doing kind of a bright field image, but we also have learned the CTF from this, right? We've learned the sign of our defocus. So we can apply that to get something that represents much more our phase of our image. And this difference might be more apparent also thinking about having more defocus. So I hope that answers the question about kind of the contrast in these sorts of reconstructions.
Thank you. Another question is about the molybdenum disulfide. Were those results, if you could potentially go back to that slide, are those obtained with the same electron dose?
Yeah, so all of these is the same 40 stem data set, just processed in different ways. So not even a different, a lot of times you might take a dark field image at the same time, and you can do correlative imaging and reconstructions that way. But this is literally from the same data set that we reconstructed, the same 40 stem data set.
I see. Thank you for answering that. So another question that just popped in is the electrostatic faceplate required as an aberration corrector for imaging?
No. So this is a good question. So we are thinking about this sort of electrostatic phase plate for a number of different applications. Where is it here? I'll leave it like this so we can see. So in theory, if you had your corrector above this, you could correct your aberrations beyond just the spherical aberrations. Maybe you're doing other aberration correction as well. And then you can insert this electrostatic phase plate and use it for helping with your tychography to make your tychography reconstructions better. Alternatively, you could think about if you don't have a spherically corrected microscope and you wanted to use something like this, you could use this for correcting these aberrations and sort of improving your resolution that way.
I see. Thank you. I actually had maybe another practical question. So it looks like that you simulate basically the contrast transfer function with respect to like the aperture like morphology, like the amount of rings, etc. So is there any like limitation of the amount of rings that you could make on this aperture? And I was just wondering like the cause and effect there for the bullseye pattern.
Yeah. So this is a very good question. So I'll think about it in a couple ways. So first, there's some in simulation, you can ask, how much better does your aberration correction get, or does your tychography get as you introduce more rings, right? Does it work better? How much better is? And then I think the second part of the question might be more what's experimentally realizable. So you can only make your crossbars so thin, and you only have such a big space in your microscope. So as we think about some realistic experimental limitations of designing these devices, that's sort of a second part of the question. And we're trying to think about what would be a happy middle. So when these simulations that I'm doing, and we see in this reconstruction, for example, where we lose our efficiency, a lot of that is going to have to do with we wanted to use realistic fill factors in these simulations. So we're using fill factors closer to 50 or 60%. But of course, it could be better if you decrease our fill factor and we add more rings, but that might not be as physically realizable. And I think that answers your question. I don't know if maybe I missed.
It does. There's definitely a lot to be explored, but
yeah, a lot to do.
Great work. Just out of curiosity, could these faceplates also be like applied to determine chiral structures in future works? Yeah, so that's something we've thought about too. So you can control, right, the phase. And there's been some really nice papers on using vortex beams for characterizing chirality. So I think EELS is one example that people think about a lot. So using this sorts of phase plate for creating a vortex beam and doing some EELS experiments is another cool application for it. I see. Great. Maybe one more. I see that there's many questions in the chat. So that's it's very engaging. Thank you all for your questions. Perhaps we'll tackle one more, and then Stephanie, maybe you can answer some of the questions in the chat afterwards. So let me pick one. Let's see. Yeah, any practical challenges for implementing these bullseye apertures? You already mentioned space. I'm also quite curious. Any other limitations that you can think of? Yeah, so I mean, I think one of the ones that we really thought about a lot and is clear in this next slide. So we actually have used something like these bullseye apertures as amplitude plates, and this is for strain mapping. So what we have at NSEM is these amplitude plates. These are bullseye patterns, and we stamp them in our probe. And the idea is for strain mapping, you want to get really accurate disk detection so you can get a better strain map. And doing sort of these cross correlation with these probe templates with these structured patterns in them leads to these better strain maps. And one thing that we've learned from these amplitude plates, and imagine something like this, but with no phase shift, is you get these long probe tails in real space here. So you can see, most of our central beam is right in the central spot here, but we do have this intensity of our probe that's sampling beyond what we really intended. So I think this is kind of something to think about and to deal with doing these sorts of phase plates and any sort of amplitude plate. You're going to have these long probe tails, and it makes a difference, especially for thicker samples. And we talk about this a bunch in the paper that we have on this as well, that's on the archive, thinking about dealing with these probe tails and their impact on thicker samples. And yeah, so as Paul said, I'll try and answer some questions in the chat, but also I'll go again to my acknowledgement slide. I have my email, and I'm happy to discuss more about these things with people if they're interested. Great. Thank you so much again for the active discussion, answering the questions, and of course your great presentation. So it looks like it's noon. So I would like to just mention a few things before we go on to our demo. Here you be able to see my screen. This is the program that we have today. So as was advertised in the afternoon, the demo was supposedly to be run on the ARM300 CF that I manage here at our NUANCE Center. However, unfortunately, we had some last-minute technical issues with the instrument. Sometimes microscopes have a life over there on their own. However, we are fully set. We have a similar setup for the continuum system in Pleasanton that our GATAN folks will run in the afternoon system. But I would just like to just mention briefly that that system is basically available here as well in our NUANCE Center. So we're an open access 24/7 hour facility. This is the Joule ARM300 stem that we have here, which, as you can see, can be operated at with the pointer at various accelerating voltages, even down to 40 kV. And from Liam, we learned that the Stella that we have as direct electron detector is really having an optimized point spread function there. So we have that available, and even though it's a non-aberration corrected microscope, we can still get very respectable resolution here. Here's a silicon dumbbells along the 1,1 ozone axis, where we can get 136 picometer that we can resolve. We have an EDS system available, and of course, what this workshop really is about is the GIF Continuum K3 with Stella system, which has the K3IS and the Stella detector available for this large range of accelerating voltages. Yeah, please keep in mind, what we'll show in the demo is also what we can do here at Northwestern. And with that, we will go on to a break now at 12:35. We will continue with the demo. The GATAN team will show the demo live at their Pleasanton location in California. And last but not least, I would say thank you again to our fantastic speakers. So please join me in giving a live or virtual applause for them. Please stick around. We'll have GATAN do the demo this afternoon. I also would like to stress, check our NUANCE website for any other events. And yeah, big thank you again for the GATAN team here to put this together, our administrative staff. Happy to have been your host. We've had students involved, and we really would like to thank you, of course, for attending.
Nicely done, Paul. Thanks, everybody. It was great to see you. I'll sign off, but you continue, Paul. Thank you.
Multimodal spectrum imaging. And as you can see, Andrew's shared the screen. So that's our F200. After that section of the demo, I'm going to be doing a little software kind of walkthrough about how to kind of process some of the data, and then we'll switch back to the microscope at the end of the session. So Andrew, it looks like you're all set up there. Are you ready to start with the acquisition part?
Yeah, we're ready to go.
Awesome.
So today we'll be working from Pleasanton. We're going to be using a JUL F200, so something kind of similar to the ARM. It's a non-probe corrected microscope, so conventional STEM. And then it's a cold filter emission gun, so it's really nice for analytical work, very high brightness source. So today we're going to be showing the continuum with the K3 and the Stella camera, so both of our flavors of direct detection. The first part of the demo will be showing 40 STEM acquisition with the Stella camera, and then we'll switch over to the K3, and then we'll show both 40 STEM and EELS acquisition with the K3 camera. The sample that we're going to be using today is courtesy of Michaela's Conroy's group at Imperial College London in the Materials Science Department. So they grew some BTFO that was doped with manganese, which is this the brighter layer here on a alumina substrate. So there's alternating layers of BTFO, and then in between those layers, there's dielectric dielectric layers of bismuth oxide. And so today we'll use this sample for the demo. Just kind of a brief software overview. So this is digital micrograph. This is the newest version of digital micrograph. It'll look like this for all versions of 3.0 with maybe some minor changes. But overall, it'll look like this. So on the left-hand side here, we have the microscope system dialog box. So this allows us to do things like open the gate valve. We can blank or unblank the beam. We can insert an EDS detector or any of the other cameras that we have from GATAN. At the very bottom here, this is all of our filter control here. So we have our ADF and BF that are on the just below the entrance aperture to the GIF. We also have the ability to switch from energy filter to EM, so imaging, to EELS through this dialog here. And then depending on how many cameras you have on the back of the GIF, you can switch between the two different cameras that you have. And then here, there's just a simple way of toggling the filter state dialog. So this allows you to do things like insert an energy selecting slit if you wanted to do that. So we're going to be doing that with our 40 stem, so we can acquire energy filtered 40 stem data. And then you can also do things like tune the GIF, center ZLP. And then we can also use this filter state dialog box in EELS mode to focus the zero loss peak so that we have the best spectral resolution possible. And then on the right-hand side here, we have our technique manager. So these are different tool palettes that we have depending on the type of data sets that we're going to acquire. So we have pretty much almost everything under the rainbow that we provide at GATAN, but we'll be focusing on the analytical TEM portion of the tool technique manager tool palette. And specifically, we'll be doing the STEM spectrum imaging. So this particular tool palette will encompass both EELS, EDS, and seabed. So this is really nice because we can acquire all of these different types of data sets in one tool palette, so we don't have to be constantly bouncing back and forth. In the workflow, the other kind of convenient thing is the workflow is the same. So we'll acquire a STEM image, we'll set up the SI acquisition, we'll take the data set, and then navigating the data, I'll show that a little bit later, but it'll pretty much be the same regardless if we're taking an EELS, seabed, or EDS spectrum image. Okay, so to get going, I'll unblink the beam. So I have the sample set up already. I'll go ahead and click view here on the scan palette. So I have the lamella already tilted to a zone axis. And then the first thing that I noticed is, so we have, we're a little bit zoomed out, but we can see larger contrast changes. If I zoom in real quick here, increase the magnification, we can see that there's these contrast changes in the ADF image, which might be interesting. We might see something in the 40 stem data. So what I want to do is I want to acquire a data set that allows us to do DPC or differential phase contrast measurements. So while I'm zoomed in right now, I'm going to go ahead and focus the image. So in the scan dialog box here, we have a little focus button here, and then that brings up a concentrated or a very small area of the screen, which allows us to look at an area of the sample at a higher resolution, so higher pixels, but a faster scan rate, so that we can focus the image and get a better image. One of the downsides about sitting next to the microscope and talking to people is that it causes the sample to vibrate a little bit. So that little distortion that you're seeing there is actually my voice. And kind of the neat thing about this microscope too is that even though it's not probe corrected, we still get a pretty decent resolution, approximately 2 angstroms. So we can resolve at least the spacing of the layers In the Y direction, it's a little bit harder to do it in the X direction just because it's a little bit out of the range of the resolution of the microscope, but still a very powerful microscope for not being probe corrected. So I unclicked the focus dialog box there, and then I'm going to zoom out because the contrast features that I'm seeing kind of stretch across the entire film there. Maybe we'll do one more click. But the nice thing is that when we do our spectrum imaging, we can specify the resolution that we want, even though we're at a lower magnification. So we can do a higher resolution scan with the spectrum image. So once I have the kind of the area surveyed, I'll switch to a slower scan speed. So when we click preview, this will be a longer dwell time. So we went from 8 microseconds to 20 microseconds. And then typically we'll have this be higher in pixel resolution. So we were at something like 256 by 256, and now we're like 512 by 512 or 1024 by 1024 pixels in the X and the Y direction. So it just gives us a little bit better spatial resolution. And then, so while that's setting up, I'll go ahead and set up our SI acquisition. So the very first thing that I'll do is while it's scanning is I'm going to access the Stella camera tool palette here. And then I'm going to go ahead and click on view. And so this will allow me to see what the aperture and the diffraction pattern look like. If I change the gamma really quick, I can see where my entrance aperture and the center of the ADF detector is. So maybe I'll just go ahead and move with the diffraction shift, I'll just go ahead and move the center of the diffraction pattern in the center of the ADF like that. And then I just want to make sure that I'm getting a relatively or a decent amount of contrast in the seabed pattern itself. So I can adjust the exposure on the Stella camera here. And so I can go higher, or smaller, or shorter or longer. I want to keep the exposure time relatively short. So I want to try to get a somewhat high resolution, so something around 5 angstroms step size. But I want to get over the entire film because I see that there are these features and contrast change throughout the whole Z direction of the film. And so we want to scan over a very large area fairly quickly so that we don't have any drift artifacts. So something like 3 or 1 millisecond should be sufficient enough. We have enough contrast in the diffraction pattern. We might be even able to go down into the hundreds of microsecond range. Actually, we can do that. So right now I'm about 800 microseconds per frame. So, and that gives me fairly decent contrast in the diffraction pattern. So I'll go ahead and unclick view there. And then I'm going to let it scan again. So then once I have the exposure time set up on the Stella camera, so I have 800 microseconds, then I'll start setting up my 2D array. So on my pixel time right here, I'm going to go ahead and enter 800 microseconds, so 0.008. And so then I know that will be a sufficient amount of time per pixel to acquire a good diffraction pattern. We will probably only need 1 pass, but we can do multiple passes if needed, depending on how sensitive maybe the sample is, if it's dose rate sensitive, or if we're using a very low probe current, maybe we need to do multiple passes. But for this particular experiment, we're just going to do 1. That should be sufficient enough. I'm going to go ahead and switch to seabed. So so we're not acquiring an EELS pattern or diffraction pattern or EELS spectra right now. And then the next thing I'll do is I'll define the size of my spectrum image. And so right now it's 16 pixels by 26 pixels in width and in height, but the step size is very large. That's 5 nanometers. So I'm going to go ahead and change that to 5 angstroms, so 0.5. Okay. So now we have 176 width in pixels of the spectrum image, and then the height is 327 pixels. And then what I did so I specified the step size, so I know the resolution that I want, which is 5 angstroms, and I locked this step size in. so that when I change this step size, the width and height in terms of pixel size of the spectrum image adjusts for that. So it'll keep the spectrum image the same across the sample, the same size, and it'll just adjust the number of pixels and the width and the height. And then it also adjusted the pixel time. So I'm going to go ahead and change that to 8. Okay, so 47 seconds. That's not too bad for acquiring a data set across the full film. I'm going to go ahead. I don't really care too much about the capping layer there, and not so much about the substrate itself either. And while I do that, it keeps the step size the same. So we don't have to constantly go back and readjust this. It'll only change the width and the height of the spectrum image in terms of the number of pixels. We have a couple other options we can view as well. So we have live view, so that we'll be able to see the diffraction pattern as it comes in as we're acquiring the spectrum image. We also have subscan, so this actually rasters the beam within the pixel rather than parking the beam right in the center of the pixel. So this is nice because it gives us a little bit higher resolution in the ADF image itself. And it also gives us a better average of what's going on within the pixel rather than just parking the beam in the center. And then if we were acquiring for a longer period of time, let's say a couple of minutes, maybe that will be more for like an EELS data set, or if we're going to do an EDS data set, we could do drift correction as well. So we could toggle this on or off. Now, the other thing when we're doing 40 STEM, which is kind of important, is we want to make sure, well, data size and data management is going to be a critical thing. So the data size for this particular data set we can read out is going to be 10 gigabytes, which isn't too bad. You know, if we were to change this to, let's say, 2 angstroms, then we go to 63 gigabytes. And then if we go to 1 angstrom, then we're probably going to go, 253 gigabytes. So we have to be a little bit careful in terms of, you know, how large the data set's going to be. So, you know, kind of an easy way of doing that is changing your step size. But if you want to maybe keep the same resolution, maybe you don't need the same number of pixels in the diffraction pattern. So we can kind of manage the data in different ways. So if I go to the preference dialog box over here, I go to seabed, we can actually software bin the diffraction pattern. So it won't help with acquisition speed, but it'll help reduce the data size. So right now I have it set to 2x binning. So it's going to take a 512 by 512 data set, and it's going to bin it in the software down to a 256 by 256 diffraction pattern. If we were to do a 1x binning here, so 512 by 512, then that will almost over double the amount of memory that we need to store the data set. So that's just kind of some things to kind of keep aware, kind of be conscious of when acquiring a 4D data set. So because I'm going to be doing a DPC measurement, I don't need a large number of pixels. And so it'll just be easier to manage the data when I'm transferring it to another computer or another hard drive. It'll just be faster, or if I'm doing it over the Ethernet. So I'm going to go back and change this back to 512 by or 256 by 256. So we reduce the data size. Okay. And then the very last thing that I want to do, if you have a thicker sample, even if it's, you know, less than an inelastic mean pre-pass thick, you can still get diffuse scattering or inelastic diffuse scattering around the diffraction pattern. And so one of the advantages of having the Stella camera or the K3 camera, or acquiring Electron or 40 STEM image using the GIF, is we can do energy filter. So we can place an energy selecting slit around the zero loss peak, and we can filter, get rid of a lot of that diffuse scattering. And that will help with the contrast of the diffraction pattern. So if we're doing something where we need to do like strain measurement, where we're looking for edge detection of the discs, and we want to know how much the discs are moving, the added benefit of the energy filter will enhance or increase the precision of the measurement of things like strain measurement or even DPC. So it's really simple to do this. So if I click view, as the beam is rastering across the sample, right now I have the energy selecting slit in. So if I go down here to the filter state dialog box, if I unclick the slit button here, it'll actually remove or increase the width of the slit. And then if I want to insert the slit, I can go ahead and insert the slit there. So you can see that there's a little bit of reduction in intensity around the diffractive disk there. I can change this width of the slit fairly easily. So right now it's 10 eV, which is fairly narrow. I can go up to 15 eV if I wanted, or 20 eV, or you can even go down to 5 eV, depending on how much filtering I want to do. Typically 10 to 15 eV is pretty good when doing energy filtered 4D STEM. Okay, so I have all my parameters set up. I'm going to go ahead and I'm going to unclick the view button here. So this will allow us, this will stop the scan at the very end of the image there. I'll go ahead and kind of position my SI right here. I'll go ahead and unclick view. And then I'm going to go ahead and click capture. So it'll buffer the amount of memory needed to store the data set in free memory, and then it'll go ahead and acquire the data set. So here we have the live view going, so we can see how the diffraction pattern is changing as we go through the specimen. We have the ADF image here with subscanning on, so we can actually see some of the layers within the sample. We can see really nicely this change in contrast that's going on within the 4D STEM data set. I also have EDS live right now, so this is a summed EDS data set. And so that's nice because we get chemical and structural information as well. And then we went a little bit, the ADF image goes a little bit faster. The data coming in from the ADF detector comes in a little bit faster than the 4D STEM data does, just because it's a larger data set. So it takes a little while for the 4D STEM data to stream in. So that's why there was a little bit of a lag there. Okay, so now our beam is blanked automatically, so we don't have to worry, or we have peace of mind that we're not doing any damage to the sample because it's parking the beam somewhere that we don't want it to park. And then we can, once we have the data set acquired, the kind of the advantage, or the one of the really nice things about doing 4D STEM and digital micrograph is we already have the tools to analyze the data. So rather than just taking a bunch of data sets and then taking all the data to your computer at a later time and figuring out, as you're analyzing the data the next day or a couple hours later, that the experimental parameters were quite right, or maybe there was too much contamination or something wasn't quite right, we can actually do the analysis now so that we can kind of modify our parameters for the next scan, or maybe we need to redo the scan. So it's really simple. If I click on the home page here, and then I navigate to our data analysis technique palette here, and I go to 4D STEM, I'll navigate back to a workspace, and then I want to do differential phase contrast. So the very first thing before I do any analysis is I want to kind of navigate through the data set, and I want to see what the diffraction patterns actually look like. So just like we would with an EELS data set, I'll right click on the diffraction SI, and then I'll click on my spectrum picker tool, and then I'll left click once that's selected. So now we have our diffraction pattern here, and then I can go through and I can just kind of see, how the diffraction pattern changes. We can go into the substrate there, into the aluminum oxide. We can go into the different layers there. We can even go into the capping layer here and just kind of see, what it looks like. It looks like the diffraction pattern. There was no hiccups. It looks like the diffraction pattern looks normal. So then once everything looks okay, I'll go ahead and I'll start my measurement. So for the DPC measurement that I'm going to do, I'll use the center of mass. So it's going to look at the entire diffraction pattern, and it'll measure how the center of mass changes across the seabed disk. So I'll go ahead and click measure, and then it's going to go through and it's going to do the measurement through the entire data set. So on the left-hand side here, we have our DX shift in the center of mass. So this on the left-hand side here. And on the right-hand side, we have our DY shift. And then if I bring I'll scoot this over here. And then I'll go ahead and I'm going to I'll bring my ADF image in the field of view and just kind of manage so we can kind of see here, I can see some contrast changes, some brighter areas in the ADF image here. And then I can see that there are some changes in both DX and DY in the center of mass analysis. So there's something going on within the layers there. So this is another layer that we can go into and analyze what's happening in our material. So depending on the number of pixels, the analysis will take longer just because there's more diffraction patterns to analyze. And then once that's done, we can go ahead and calculate our vector displacement. So we'll get a dialog box here that asks us what's the displacement in the x direction. So the measured displacement is the dx from center of mass, and then our y displacement is the dy from center of mass. I'll go ahead and click OK. So now we have our vector diagram here. Let me go ahead and change the contrast a little bit. So we can see that we have, so this little color wheel here shows us which way the center of mass is changing as a function of position across the film here. And so anything that's in pink is being deflected in the kind of the negative x direction, positive y direction, and then anything in like dark blue is pretty much in the y direction, and then so on and so forth. And then we can get what the gradient is. So how large of a shift, not just in terms of what the direction is, but what's the magnitude. So I can go ahead and calculate that. And then if I change my contrast level here, we can see that there's a larger shift or larger gradient of the shift in the same area that we observed this contrast in the ADF image there. And then we'd have to do some deeper digging in terms of how does that affect things like the topology. So the idea behind these thin films is that you can engineer polar vortices through strain engineering. And so maybe we would, if we had a probe corrected microscope, we could go through and see what does the atomic structure look like, within these layers here, or maybe there's something going on in terms of like the polarization. So maybe we have some domain, a different domain in this area where we have the brighter contrast in the ADF, and where we see these larger gradients in the center of mass shift in the diffraction pattern. Maybe there's something going on with the polarization. Maybe we have a domain here versus on either side of the of this area here. Okay, so that was really quick. If we were taking a data set, we would say, okay, this data looks, we did our initial analysis. The data looks sufficient enough, and it's high enough quality that I would go ahead and save this. The nice thing about digital micrograph is it automatically puts all of your new data into a different workspace. And so this is really convenient because I can just save the workspace as it is, and I can go ahead and save the data as I want. And then it'll automatically save everything for us. So all this data, all the raw data will be automatically written for us. We don't have to save everything individually. And then because this is a larger data set, I'm going to go ahead and close it so that we free some free memory space for the subsequent data sets that we're going to be acquiring. Okay, so we took some data with the Stella camera. Now I'm going to switch over to the K3 camera. So it's very simple. We don't have to change anything in terms of the STEM imaging. I'll just go ahead and right click on the K3. I'm going to go ahead and select the K3 as my primary camera. So it's acquiring a sync. So it's making sure that we can read out the areas of the sensor. And then once the K3 goes blue, I'll go ahead and right click and click insert. So I don't know if you can hear that, but there's a rush of air. So basically there's a pneumatic drive that's inserting the K3 into the optic path of the spectrometer. So the K3 has to be inserted because it sits in front of the Stella, and then it's retracted when we're using the Stella. Okay, so we can take a similar data set as we did with the as we did with the Stella, as we did with the K3. But going back to the discussion of data management, the K3 is a 3,456 pixel by 3,456 pixel array sensor. And so that's quite a large array size to be storing. So just to kind of display, let's see here. So I'll go ahead and click view. Let me go ahead and research. So if I go ahead and click view here, so I have I'll go ahead and view the full sensor array. Okay. So one kind of side note here is that the K3 functions a little bit different than the Stella camera. So we have we can read different areas of the sensor. So we can reduce the number of pixels that we're storing in the seabed pattern. We can also bin the sensor. We can do both of those things on the Stella camera, but there's more what we call ROIs, or region of interest, on the K3, just because it's such a larger sensor size. So we have more. We can do a half ROI, or we can do a quarter ROI, or we can do 1/16 ROI. And then the smaller the ROI, the faster we can read the sensor out. So the faster we can acquire a spectrum image, while acquiring 40 STEM. And that's just because we don't have to read as many pixels out for a smaller ROI size. So depending on the experiment that you're going to be doing, typically for 40 STEM, we don't use the full sensor size just because the readout's slower. So typically we're operating more in like the quarter or the 1/16 ROI size, depending on what, if you're going to be looking at a very small convergence hanger, you're going to be doing like a strain analysis, orientation analysis versus like a DPC measurement. You can alter the sensor, or you can alter the readout of the sensor to optimize for those conditions. And then the other thing that's different from the Stella camera on the K3 is that there's a live time. So the K3 is much more sensitive, or has a much lower dynamic range than the Stella camera does. And so it saturates much faster. And so we have to kind of throttle the intensity of the beam sometimes using the live time. So this live time will enable the fast shutter above at the very top of the entrance aperture, or at the very top above the prism and the spectrometer. So this will blank the beam for a given amount of time. And so this live time is basically a percentage of one frame. And so if we're reading out a full sensor on the K3 camera, this is 15% of 600 microseconds. Or no, excuse me, 6 milliseconds. And then depending on the ROIs, that frame time will decrease. But what this does is it allows us to stay under the counting limit. So I have my little ROI tool right here. And if we go down to the very bottom here, we can see the number of electrons per pixel per second that's hitting the sensor in this particular area. So if I go to, let's say, 30%, we'll actually go, actually that's a little bit, let's go all the way to, we'll go to 60. So now we can see that the numbers start turning red in some areas as it scans across the sample. So the counting threshold, so the limit at which we can detect individual electrons coming in is 80 electrons per pixel per second. And then when we go into areas that are 100 or over 80, we start getting these red numbers down here. So that's just basically telling us that we're over the counting threshold. We're not damaging the sensor, but we're not as sensitive as we could be. So we're not taking full advantage of the DQE of the sensor itself. So we can use the live time or the fast shutter on the spectrometer to stay at or below that counting threshold there. So I'm going to go ahead and change that maybe back to 40. So we want to kind of optimize this so we get the largest amount of intensity without going above the counting threshold there. So I'm going to maybe 50%. Yeah, I think that'll be good. So we're going over a little bit in the thinner areas up here, but we're staying below the counting threshold in these areas here. So I'm going to go ahead and stick with 50%. And then for my exposure time, we will change that after I look. Let me change the ROI. So like I was saying earlier, let's see if I go to 2D array. And just in this example, so if I try to acquire a 40 stem data set from the same area, and we were using 5 angstroms, so 0.05. So for the same or roughly the same array size using the full sensor, the data set's going to be 253 gigabytes, so much larger. That's going to be really hard to deal with. That's right at the limit or just above the limit of what we have in terms of free memory on the computer. So it'll probably crash the data acquisition. So we won't be able to buffer that amount of data. So we need to change something in the acquisition so that we can have a data set that's more easily managed. So I don't need this many pixels as we saw with the Stella camera. So I can probably go to a quarter ROI. So I'm going to go ahead and change the ROI to readout mode there. So it's acquiring a new sync because we're reading out from a different area of the sensor. Okay, so we can see here too that we have a much larger, so the diffraction pattern takes up a much larger portion of this particular area. So I need to change the camera length. So that's not too difficult. So I'm going to actually change. So right now I'm using a 50 millimeter camera length. I'm going to reduce this down to 25 millimeters. And then it's just as easy as we're going to go ahead and just shift this back onto the center of the sensor there. So that should be sufficient enough for center of mass. So now we've reduced the data size down to 22 gigabytes. I can further bin this data set if I wanted to. So if I go to seabed pattern, I can do 512 by 512, or we were actually doing 256 by 256 on the Stella camera, so that should be sufficient enough. So now we're much lower than we were before. And so now that I have this, I have my energy selecting slit in, so we don't have to adjust anything there. And then I'm just gonna go ahead and adjust my exposure time to be a little bit faster. There we go, that should be sufficient. That's good. Okay, so that should be good. We're running at full frame, full speed. We can actually go a little bit faster. So with the diffraction pattern, we can go out of counting mode. So if we go into high speed mode, we sacrifice a little bit in terms of sensitivity, but we can go a little bit faster. And so typically with the diffraction pattern, we have such a high intensity, especially in the direct spot, that we don't necessarily need the counting sensitivity of the high sensitivity of the camera itself. And sometimes we want to we'll sacrifice a little bit of sensitivity to go faster. And so we can switch into high speed mode, and then this will allow us to actually go a little bit faster. So our kind of ceiling or lowest limit on the exposure was 3 microseconds with high speed off. Now with high speed on, we can go down to basically 800 microseconds like we were with the K3 camera. And so, but because we don't have quite the dynamic range, the diffraction pattern is a little bit noisier. But that's okay. So we can do we could do 2 passes instead of 1 pass. So it'll take a little bit longer to acquire the data set, but it's fast enough that we shouldn't see any drift. The stage is pretty stable, but we might kind of have to go at it a little bit different way in terms of increasing the dynamic range with a K3 camera. So it acquires, we can still obtain the same dynamic range, but we have to add more frames together in order to get to that point there. Okay, so I'm going to go ahead and delete this. This is our live view here. Oh, switch that. Okay, so I'm going to go ahead and I'm going to stop this. It's a little bit distracting. I'm going to change my ROI again. Change this. We'll go 5 angstroms. I have 8 micron. We have a 800 microsecond dwell time. We'll do 2 passes. I'll go ahead and stop the scan, and then we'll go ahead and click capture. Now we could potentially go even faster than this with the 1/16 ROI. But the only issue is that on our microscope, the standard camera lengths don't allow us to see the entire center spot of the central disk of the seabed pattern. So we would have to come up with a custom camera length so that we could get all this diffraction pattern in there. So the lowest that we can go is 15 centimeters nominally, and so we'd probably have to have like a custom camera length that was like 5 centimeters or 2 centimeters to get everything within the field of view of the camera. So we could potentially go faster, and we don't necessarily need the number of pixels for this particular data set. And then we can kind of see here that there is some lag in the ADF image completing and the diffraction SI completing. And that's just because it takes longer for us to stream the diffraction pattern than it does for the ADF image to acquire the data. So I'll go ahead and, once it's finished, I'll go ahead and stop that. And we can see there that there's still data streaming coming in. The data set's acquired, it just takes longer for it to come into to read out into the software. We can also see the same contrast changes that we were seeing in the Stella camera as we do with the K3 camera. Another thing that I forgot to mention is we could also bin the sensor itself. So we can actually physically bin the sensor rather than just doing software binning. So if I clicked 2x here, then that might give us a little bit better signal to noise on the diffraction on the pattern itself. And so that would allow us to still keep the same dwell time, but maybe we wouldn't have to do 2 passes, do 1. And actually 1 pass seemed to be sufficient enough. So, with 2x binning, we could probably keep it at 800 microseconds. So similar acquisition times as the Stella camera there, but maybe just a little bit more flexibility in terms of how many pixels you want to have in the diffraction pattern. So there's some give and take there in terms of advantages and disadvantages of each one. Okay, so the nice thing about the K3 camera, especially operating at the higher accelerating voltages, so 200, 300 kV, is that the K3 has a very narrow point spread function. So this is really good for EELS. And so once we've acquired a 40 stem data set, we can easily switch over into EELS. And so I'm going to go, so it's just as simple as going from FTEM, so energy filtered mode, into EELS mode. So now that we'll switch the post-slit lenses so that we're projecting spectra onto the K3 camera rather than a diffraction pattern. Okay, so like I was saying earlier, one of the advantages of having the K3 camera is that it has a very narrow point spread function for 200 kilovolts. And so the advantage of that is that we can have a very large spectral range, so a very low dispersion, but we can still maintain a decent energy resolution. So, and also because we have more pixels on the K3 camera, we can go further out in energy at a lower little bit higher dispersion. And so with 0.9 EV per channel, we get about 3,000 EV pixel range, and we have the point spread at 200 kilovolts is about 1 pixel wide, and so we're which is, you know, we're about 0.9 EV per channel, which is, you know, within the, if we had a like an XFAG or a shock emitter, you know, that we would, the pixel resolution would still be better than the full width half maximum of the energy spread of the source itself. But one of the advantages, so let's see, so I have 0.9 EV. I'm going to go ahead and I'll view the zero loss first. So the advantage of having such a lower dispersion and a large number of pixels on the K3 cameras, we can go very high in energy range. So we're starting here. We're starting at 0 and we can go all the way out to 2900. And if we do dual EELS, then we can extend that out even further. So that's really nice because in this particular sample, we have titanium, oxygen, manganese, and iron, which are all really close to one another. But then there's also aluminum and bismuth, and those are at higher energies. And so if we were using a smaller dispersion, we might not necessarily be able to access the bismuth M edge or the aluminum K edge. Okay, so I have my zero loss peak there. We have where the full width half maximum of the zero loss peak, because the point spread function is so good, is 0.9 EV. So the energy spread at the particular conditions that we're using of our cold field mission gun is about 0.53 EV. So we're actually limited more by the dispersion that we're using than we are the energy spread of the cold FEG. Okay, so I already aligned the ZLP earlier. So the nice thing, one of the nice things about the continuum is it's very stable. So we can go back from FTEM to EELS very fluidly. We don't have to do a lot of tuning or adjusting of the ZLP. And so now I can just go right into dual EELS. So I'll go ahead and change. So I'm going to have my high loss be at 400 EV. My low loss will be at 0 EV. So we have the zero loss peak. And then I'll go ahead. My lifetime we can adjust separately or independently from the whole loss, the low loss to the high loss. So I'll have my lifetime be about 0.2 EV. That'll keep us below the counting threshold in the low loss region. And then in the high loss region, I'm going to set it to 100%. So now we're taking full advantage of the, we're running at 100% duty cycle. So we're taking full advantage of all the electrons that are hitting the sensor, and we're not blanking the beam. Okay, so we have the low loss and the high loss set up. So we're going to be able to acquire basically the carbon K edge all the way out to the bismuth edge, which is over here, which you can barely see, but it's just a little bit of a shoulder there. And then I also want to make sure that we are no longer in high speed mode. Take that out. I'm going to go ahead and refresh my scan area again. Looks like there might be a little bit of drift in focus, so I'm going to go ahead and I'll keep everything the same. Adjust my focus a little bit. Looks pretty good. And then typically an EELS data set will take longer than the 40 STEM data set. So I'm going to use spatial drift. So we're going to use drift correction to make sure that the sample and the ROI stay in the same spot. And I'm going to use this little area here. This will be a nice area to do the pre-drift measurement there. We can use the same step size. We can keep it at 5 angstroms. I'll do a pixel dwell time of about a millisecond. Oops, 0.001. And then we want to do multiple passes. So the nice thing about the K3 camera is we can count electrons. We have single electron sensitivity. And so when we set the sensor up that way, the only noise or source of noise that we're dealing with is Spillane noise. And so basically we can get over that, or we can improve that the signal to noise ratio by adding more frames together without paying a penalty for like read noise that you would have in an optically coupled camera. And so it's actually more advantageous to sum multiple frames together rather than taking one long scan. So because we have the sensitivity, we can add frames without paying a noise penalty. We can scan very fast. And because we can scan very fast, so we can do one pass of the spectrum image so if you do one pass, it's going to take us 54 seconds. And within that time, we can monitor the position and the condition of the sample. So we can make sure that there's no damage going on, there's no contamination. And then that also allows us to correct for drift between frames. And so if we were to do a very slow scan with one single pass, we might get maybe a quarter or halfway through the spectrum image and realize, oh, the sample is damaging, or we've drifted too much, and maybe we're already 3 or 4 minutes into the acquisition, we'd have to start all over again. But with multipass spectrum imaging, we have constant feedback of the condition of the sample, position of the sample. So just more advantageous with the counting cameras to do this multipass acquisition. So we would probably do something maybe more like 10 passes. And I have the live acquisition, so we can see the spectra as they come in. I have drift correction enabled. We have sub-scanning enabled. I'm going to go ahead and switch from seabed to EELS, so that we're acquiring the spectrum, the EELS spectra instead of the diffraction patterns. And then the nice thing about having EDS is that they complement one another. So if we're acquiring EELS, we can also acquire EDS simultaneously. And let's see, so I will stop talking. Finish the scan, and then one other thing that's very important when doing multipass spectrum imaging, we want to have ZLP lock on. So in the EELS palette, the ZLP lock will actually monitor the position of the zero loss peak, and it'll adjust it as there's any drift. This is important, especially because I'm sitting next to the microscope, and so if I move my chair just a little bit or move a little bit, there'll be some adjustment with the there could be a little bit of drift with the centering of the zero loss peak. So it's important to have this ZLP lock enabled when we're doing multipass spectrum imaging. I'll go ahead and click capture. So we're gonna, it'll look at this at the pre-drift measurement. It'll take an initial image, and then it'll see how much drift has occurred in the image over a given period of time. And then once it's measured the drift from that initial image, then it'll make an adjustment in where it scans the beam, and then it'll start the spectrum image acquisition. So we have our ADF live ADF image here. Because we have sub-scanning on, we can actually see the individual layers, even though we're a very high field of view. I'm talking, so that's why we're seeing this chatter in the live ADF image, unfortunately. And then we have our low loss region here, our high loss region, and then our EDS spectra, and then our spatial drift measurements are kind of always running in the background there. And then reduce these guys here. And then we can navigate through the data as we're acquiring data. So we just finished the first pass, now it's going through the second pass. If I use my spectrum picker tool, I can go through and navigate through the data. So I have to kind of sum a fair number of pixels together right now because we just haven't acquired long enough. But we can see, here's the bismuth M edge. If I right click on the image, I say add to quant, it'll actually show me where the edge onset of bismuth is right there. So it's an M edge, so it has a very delayed broad hump. And then if I go down to the substrate here, I should be able to see the aluminum K edge pop up there. And then if I go over to the low loss or the lower energy region here, I have the oxygen K edge. Carbon K edge is always kind of present because there's some carbon contamination there. And then if I go through, we can see there's the oxygen K edge, the titanium edge. If I sum over enough pixels, there is some manganese there. There's the iron L23 edge. If I go up into the capping layer there, chromium pops up. And then on and so forth and so forth. Okay, so for the instance of time, for interest of time, I think we're kind of running short. We're getting kind of close to this first part of the practical workshop ending. So I'm going to go ahead. I'll let the scan finish. So the nice thing about spectrum imaging is we can add more passes. So let's say we got to the 9th pass and we saw that maybe the signal to noise wasn't quite high enough. So we can actually increase the number of passes on the fly. Or if we see that we want to stop the spectrum image, or maybe the signal to noise is sufficient enough and we have a very beam sensitive sample, we don't want to keep irradiating the sample, we can actually click capture, and then it'll stop the spectrum image once it's done with the last pass. And so it's very flexible. So we can add more passes, we can stop at a certain pass. We don't have to, we're not set hard. It's not set in stone with the number of passes before when we first set this up before the acquisition occurs. Okay, and then again, so I have a kind of I took a data set from a different area. So just for the interest of times, we don't really have the 10 or 11 minutes, so I'll let that kind of play through. But I took the spectrum image from a different area of the sample here. So we have our ADF image here. We can resolve the different layers. We have our low loss. We have our high loss. And then we can navigate over to, so if I click on this area here, we can navigate to our spectrum image. And then we can highlight where the different ionization edges are at. We use the splitter tool here so we can kind of see, okay, we have bismuth. We have our lower energy edges here. And then, so what I did was I made a recipe here in the quantification. And so what this does is it'll set up a recipe post acquisition. So I've already set all the MLS fitting up for the different ionization edges here. And then I've saved this in a repository. And if I want to load it, I have it just as BTFO here, and it'll automatically load this particular recipe every single time. So that's really nice, especially if you're doing something like process control and you want to do the same analysis over and over again. And then if I go ahead and click on map, we can choose, I'll go ahead and we'll do the edge integral, and then we'll do volumetric density. And then I'll go ahead and compute the maps for us. So we get fast feedback of what the data sets look like on the fly there. And so I don't know why that looked a little bit better here. Yeah. So so this is the same data set, but it was, yeah, I don't know why that turned out differently. But anyways, so this is the same data set that we had here. Let me get the ADF image, copy. And so even, the cool thing, so with the K-through camera, because we have a fairly high sensitivity, we can acquire, because we have a high sensitivity, we can acquire very fast. We can do multi-pass spectrum imaging. It allows us to monitor and correct for drift and get rapid feedback about sample drift. We can still resolve the layers, at least the larger spacing within the BTFO layers. And we can see, the chemical distribution on a very large, somewhat large scale. And so we can actually see, there's in one of the layers here, we can actually see there's an enrichment of the aluminum and a deficiency in the manganese, as well as the iron and the aluminum. The bismuth is a little bit more noisy because it's just a higher energy edge. The cross section is a little bit lower. You can see a little bit maybe of enrichment here in a different area of the film, but yeah, so we can get really rapid feedback. So we will acquire 40 STEM data of the sample. So we get structural information. If the DPC may show things about domain boundaries, that gives us a little bit of information about the functional properties of the material. With that mode of data acquisition or data mode of data, and then with the EELS and the EDS, we can link the functional properties and the structural properties with changes in chemistry. So maybe we'll see some deficiency because we see enrichment in titanium, but deficiency in manganese and iron in this layer. Maybe there's going to be some changes to the structure or the functional properties of the material because of that. And so that's kind of the nice thing about having the acquiring 40 STEM with the GIF is that we get kind of the whole picture of the entire package in one go. So within an hour we got 40 STEM data, we did DPC analysis, we got EELS data set, and we were able to do EELS acquisition, and so we have a very complete picture of our sample. So that's all I have for this particular section of the practicals. Were there any questions about this part of the session, Liam, or did we want to move on to the data processing part?
Yeah, thanks, Andrew. That was a really nice demo. So no real big questions came in. Just one question came in relating to the script that I described in my presentation. And someone was just asking if we can use that on other systems. So just in case the wider group didn't read the answer, the script is basically going to run on any continuum GIF. So that means in any digital micrograph version that's 3.4 and higher. So it's currently not published. I'm just going through some final testing, but I'm expecting to make that like freely available probably in the next quarter, so sometime later in the summer. Yes. Okay, so I guess I can take over then in that case.
Okay.
Yeah, and we can do some stuff with digital micrograph with some software. So I will go ahead and share my screen. Can you see digital micrograph? Just as yeah.
Very clearly, yeah.
Okay, perfect. Thanks for the confirmation. Right, okay, so continuing on the theme of multimodal spectrum imaging, I've just got a data set open here so we can walk through some of the kind of the post-acquisition processing steps or things that we might want to do once we actually have the data. So just kind of as an introduction, what are we looking at? Okay, so I'm using an offline installation of the software. So it's digital micrograph 3.6. Same as Andrew was using on the microscope, but I don't have any hardware control because I'm using a computer that's not attached to the microscope. So no microscope UI on the left, and then the technique manager on the right is significantly reduced with respect to what we saw on the microscope. Okay, so the data, so what are we looking at? So this is a multimodal experiment that we performed on carbon nanohorns that are like doped with gadolinium. So what's that? So it's a carbon-based material. So essentially like the fibers of like nanotubes, and then there's some metal oxide kind of distributed within the nanotube kind of bundles here. So yeah, it's a carbon-based material. So our goal here was to work in a regime where we weren't going to get knock-on damage primarily. That's the primary damage mechanism for like graphene or like carbon nanotubes. So we were running here at 60 kV beam energy, and because we were running at 60 kV, we decided to, well, we used the Stellar. So this is data from the hybrid pixel camera, the Stellar detector. Right, so what's the data that we have? So we have the survey image here on the left. That's just our ADF signal. And then just kind of moving across to the right, we have a ADF image that was acquired like alongside like spectrum image data. And then we have low loss EELS and high loss EELS, so dual EELS pair. These would have been acquired at the same time. And then we have a 4D STEM data set as well from the same area. The way that the experiment was done, essentially what you do is you set up your spectrum image and choose the array area, like the pixel density and so on, like we saw earlier. And then the thing that's important is that we have spatial drift correction enabled, and it's basically on a region that we are like confident where that drift correction is going to work. So the workflow is we capture our EEL spectrum image, so our dual EEL data set, leave the spatial drift correction on, change the filter to F10 mode so that we're going to have 4D STEM, and then we just literally hit capture again. The software makes a drift measurement at the beginning of the experiment from the exact same region. So we're basically having good spatial correlation between our EELS and our 4D STEM data within kind of the constraints of that drift correction working. So that's kind of the workflow. That's how you get this data set. And then it's important that the pixel array is the same size if you want to make it really, really nice. So we can see if I select the 4D STEM data set, it's 128 by 128. So that's actually the reciprocal space dimensions. Our real space, we're looking at 140 by 193. And then that's the same. Our EELS is the same. Our other EELS is the same. One thing that's interesting, if we look at the ADF, you can see that the ADF is actually bigger in terms of the pixel array than our kind of our analytical data. The reason being is that we have we did this with subpixel scanning, and what you can do, as Andrew showed, I think you can essentially you have a mosaic mode, and you get all of the subpixels like in the subpixel scan image. So you can have an ADF image that's like higher pixel resolution than your EELS or your 4D STEM, which can be quite, there's like loads of reasons why that's useful. Right, okay, so how do we look at the data? So we have some bread and butter tools that we're like familiar with, or we should be familiar with. One of which is the spectrum picker tool. So you right click, and then you have this little box at the top, which is like a little cube with a red arrow on there. So before I go ahead and actually extract some data, I'm going to just go into the analytical technique, because that's contains most things that I'm interested in for now. So analytical. So I've got EELS quantification, and I can do things like mapping and so forth. So I'm going to start off with the low loss data set. Right click, picker, and then I just draw a picker region on that spectrum image. What does that do? That extracts some, in this case, like spectral data from this low loss spectrum image. So at the moment, it's just a single pixel. I move that around, that spectrum gets updated, and we can just then also increase the size of the picker ROI if we want. So instead of just having a single spectrum, it's just the sum of all the spectra that are enclosed by that red box that I have there. Okay, so that's our first tool. Then the second tool that we always use is the slice. So remember, this is like essentially a three-dimensional data set. So you've got spatial dimensions in X and Y, and then energy loss is our Z direction. So it's going to be the depth of the cube. So we obviously can't see a 3D object on the screen. So what we're looking at here is some integrated range of intensity, and that's what's being displayed here. So if we go over to the palettes on the left, you've got the slice, and you can just change that slice around and the contrast changes, okay? So you've got two sliders. One is just the slice position and one is the slice width. If we want to know like what we're actually looking at, just select the spectrum and then hit show range, and then you can see that slice. So we're integrating in the sort of plasmon region there on that low loss spectrum. I can make this a little narrower. And then if we switch to the zero loss peak, you can see an obvious change. It's kind of akin to a bright field image. I'm just integrating the zero loss peak now, and then you see the contrast flip. So that's kind of how we navigate the data. So we pretty much like bounce between using these picker tools and these slice tools. So the first thing that we would always do with the dual EELS data set is we want to make sure that our energy like scale is good. So 9 times out of 10, if we're doing dual EELS, like one of the spectral pairs is going to be a low loss data set. So it's useful to get the low loss data for like two main reasons. One, it acts as an energy calibration. We have 0 because we have the zero loss peak. And so we can use that to calibrate both this spectrum image and the high loss spectrum image. And then we also have the low loss information, which gives us information about like pleural scattering that would be in the high loss spectrum. So super straightforward to do an energy correction. First of all, we just draw, basically you just draw an ROI over the zero loss peak. And then we go to SI, align SI by peak. Now, I've already done this with this data set. I can show you just easily by eye. So if we draw an ROI alongside the zero loss peak, we can just move. So you'll get the biggest energy shift, like usually corner to corner. And I can see that that zero loss peak is not drifting at all. It's already corrected, or I probably had zero loss peak lock on when I acquired the data. Right, so one thing that's pretty cool actually while we're looking at the zero loss peak here is you can see like the sharp point spread function of the hybrid pixel detector at low kV. So 60 kV, we really expect to be able to get single channel full width half max like out of the detector at like anything less than 80 kV. So what do we have? We're 38, yeah, around there. Yeah, so our step size is 0.8 eV, the dispersion's 0.8 eV, the energy resolution of the FEG, as I said earlier, the cold FEG is close to 0.4, maybe slightly better at 60 kV. So we're getting single channel energy resolution. So this is like kind of the best case scenario. So we're maximizing energy field of view and we are kind of maintaining resolution. One thing that is, again, like I'm still here is like very kind of cool with the hybrid pixel detector. You have like really good like black level. So I'm in vacuum. The only thing we really have there is the zero loss peak. The dark is really like quite truly dark for these hybrid pixel detectors. It's pretty impressive. So I'm just clicking on a few buttons. Okay, so what do we want to do next? Okay, so actually we're probably primarily more interested in the high loss data for this data set, but let's just kind of move out of vacuum and just expand my spectrum somewhat. So zero loss peak, plasmon peak. So final kind of cool thing with the hybrid pixel detectors is that, right, as we said, like they have like really big dynamic range. Okay, so we've got this zero loss peak, which is obviously super bright compared to low loss information, even brighter compared to anything in high loss, right? But because we have like pretty high dynamic range, we're able to, once we've summed a few frames, so what are we looking at here? So that's like 780 frames summed, which in terms of absolute time, still pretty fast, okay? So 70 milliseconds, or yeah, 70 milliseconds of data. So really not much. we're able to see the carbon K edge. Gadolinium, I think it's an N edge here at 140 eV, but you know, we still are sort of constrained. We do need to fit this in the ceiling of our dynamic range. So that's why in this case I did dual EELS, because we have the spectral features that we want just actually in a single spectrum, but we're constrained with our exposure time because of the low loss and the zero loss peak. Right, how do we get our high loss information? Now, the way I like to do that most conveniently is we just grab this picker tool that we already have on the low loss, and then we just drag it onto the high loss. And that creates what's called a mirrored picker ROI. So really easy, just drag it and drop. Those are then linked. And so we know that we're getting the same number of spectra sums, exact same position. So you can see we have like much better SNR in the high loss. The reason is just that these frames are longer. So we're just summing more. Yeah, so this looks like it's about a factor of 10x what I did for the low loss spectrum there. So not surprising, we have like much cleaner spectra here for our N and our gadolinium and our carbon. So one thing that's like bread and butter tool that we'll do with the high loss is we might want to take a quick look at just an ionization edge, see how it changes. So we just control, click and drag, and that's just a shortcut for a background window. So it's just fitting a power law to this pre-edge region that I've defined for carbon, and we can then just have a very quick look at what we kind of think the carbon fine structure is going to look like. So if we kind of look around here, it looks like there's actually quite a lot of changes going on. But we have to be a little bit careful, okay? So this is a carbon-based material, so we don't expect there to be much in the way of scattering. It's pretty thin, low Z. But we are at lower KV, so there is more scattering because the mean free path can be longer. And then if we just look at this, you can see like this looks a lot more electron transparent here just by eye than in the center here. So we need to be a little bit careful before we try and draw any meaningful conclusions from just looking at the rough edge shape. Super easy thing to do is to just go over to our EELS analysis palette here on the right, and we have a number of like useful processing tools. So one of them is deconvolve. So if we do deconvolve, it just does a nice live Fourier ratio deconvolution of that carbon K edge. So that's what we're looking at with the pink spectrum there. So this is a single scattering distribution of our carbon signal. So we're removing any plural scattering. Reason that we can do that is because it's this multimodal data set, and we have a low loss and a high loss pair. Software just does it all for us. So we can just move the picker around and then see what happens. And if we look at the deconvolved spectrum, you can see actually there isn't really that much change in fine structure of the carbon at all. What I was looking at was really just plural scattering. So it's pretty important to have the low loss information available so that you can make these corrections. And you can do it live on the fly as we're looking at the data. So I've done this kind of in reverse. I've just jumped straight in and looked at the core loss spectrum. So something that we should really routinely do first is actually to just make a relative thickness measurement on the low loss spectrum. So you can do that on the map. You can also just do it on the extracted spectrum. The same tool over here. So EELS analysis, hit thickness. And then as I move that picker around, you can easily see where you are with respect to kind of your relative thickness, which is really just a measure of how much multiple scattering we have or don't in the data. Okay, so we've kind of just done a quick survey of the image or the EELS data sets. So what can we do next? So we've got carbon, we've got gadolinium. if we want to do some mapping, that seems like a reasonable thing to do. So how do I do that? So let's do some elemental mapping. I'm going to minimize some of these data sets that I've just thrown around everywhere. So if we want to do mapping, all we need to do is work with a high loss data set. And we just have an extracted high loss spectrum. And then we just add some elements to the quantification list. So it looks like I already did that with this data. So I'm just going to take those out. Imagine that they're not there. Right click, clean the spectrum. So this is just the, the as extracted data. So you've got two approaches that you can adopt here. You can either like try and figure out what's in the sample if you don't know by like clicking near spectral features. There's this button that says add to quant, and it makes suggestions of ionization edges that will just lie near that exact energy channel that I selected there. So carbon is suggested to me there. And then that will be the same for the gadolinium at lower energy. So gadolinium. If we already know what we have in the sample, we can actually just go right ahead and use this periodic table and this elemental quantification palette. And just add our elements from here or our ionization edges. So carbon just has a single option. So it's carbon K. And gadolinium is going to take me some time to find. I think I'm just going to add it here. Add to quant, gadolinium. Oh, there we go. Right, so it's in the bottom row. So it's actually just grayed out for me because I've got unusual elements kind of selected to be hidden, which I probably don't want to do. And it would have been easier to see that. Okay, so we have the two elements in the quant list. We can just look at the edge setup. So always, how does this work? So it's doing linearly squares fitting with two components. You've got a background model and then an edge model. So we'll start with the carbon because that's simpler in this case. So carbon, we have by default, it's going to be a Hartree Slater cross-section shape for our edge component. So that's what we're looking at here. You've got this option that says include plural scattering. Usually, like this is going to be on by default because the software knows that this is part of a dual EELS pair, which is saying, okay, I can do plural scattering correction for you. That's generally a good idea. This is switched on. And that's why this has this sort of modulated shape. If you switch that off, then it just has the basic K shape there. You can see that the fit is generally, like the overall fit is better with plural scattering correction turned on. And then what we're doing is we're excluding the LNES region because the basic cross-section shape doesn't have any like near edge structure in that model. So it's better to not fit in that region. And that's why we see this different color here. So the carbon looks fine. Gadolinium. Now the gadolinium's a little bit more, well, it's not really tricky, but like we got to bear in mind that this is an N edge. Okay, so the calculated cross-section shape for the N edge is not particularly good. So we have generally like the calculated cross-section shapes for K and L edges are not too bad, but as you go up higher, the calculations just get poorer. So instead for my gadolinium, I can use a standard, which is something that I extracted like from a gadolinium reference, and then that should fit a bit better. We also need to be a little bit more careful with the background fit region here because it becomes less and less power law like as you go to lower energy loss. So I'm just going to decrease that kind of fit region a little bit to account for that fact. Okay, so that's pretty much it. So I hit map. We've got multiple options for mapping. I'm just going to run with areal density, hit OK. And then we end up with 2 elemental maps in a new workspace, one for carbon, one for gadolinium. super straightforward to do a composite. We just use this color mix tool, add the color mix, and hit OK. There we go. So that allows us to very quickly see the relative distribution of the gadolinium in the carbon, like kind of the carbon material there. So I'm going to move that back to the primary workspace because it might be useful for us. So we just move to workspace, put it in gadolinium nanohorn, and then just go back over here and then do the same steps again. So let's just tidy up a bit. Right. Okay. So done some stuff with the EELS data. So we've got some elemental maps. This is probably quite a nice point to look at the 4D STEM data. So the 4D STEM data in terms of so this is a 4-dimensional data set instead of a 3-dimensional data set. We have convergent diffraction patterns at each pixel position instead of EELS spectra, right? But in terms of the software tools that we use, they're the same. So we can use the picker tool. If we drag it onto our 4D STEM data set, it just extracts a diffraction pattern for us, or a sum of diffraction patterns. So this is all the diffraction patterns that are enclosed in that region. Okay, so it's not like I need to completely relearn everything because I'm doing 4D STEM. Like the workflow and the tools are basically same or identical, just with an extra dimension of data. Similarly, we can use the slice tool, right? So we move this. Okay. Question? Oh, okay, I'll continue. So I have some extracted diffraction data. I can use the slice tool just as I did for EELS. We just have more sliders, okay, because we have an extra dimension. So 2 axes and then 2 extents in those dimensions. So here you really want to use show range. It makes it much easier. So you just select the diffraction pattern, hit show range, and you can see the reciprocal space range that we're integrating to give us the contrast in the actual 4D STEM data set to the left. So what I'm looking at is it's essentially a virtual bright field image. If I move that somewhere else, completely changes. It's because I have auto survey switched off on this one, because that contrast is preferable for me. So I'm probably, yeah, you can see how it changes. I'm not going to switch auto survey off because it will ruin my beautiful yellow, green, blue image there. But you kind of get the idea. So one thing that's useful when we're looking at the extracted diffraction patterns, you really want to make use of the histogram over here and the controls. So more often than not, the dynamic range that you have in diffraction data is way higher than what could comfortably be displayed on the screen. So you only have 256 gray levels on a computer screen. And the data has thousands or tens of thousands of gray levels. So the thing that I always do is I just go over to this histogram and then you can just draw on it. So I'm left clicking and dragging, and you see this this gray highlighted box. That's basically just re-evaluating what is the high and the low. So the white level is to the right hand side of that box that I just drew, and the black level is to the left. So it's just going to boost the intensity there. So you can see the contrast looks a little bit saturated in the bright field disk, but we're now able to see information out to higher order in the diffraction kind of domain. There's not much going on here because I'm just parked in an amorphous region of the nanohorn. But if I move over some of the gadolinium regions, then you start to see interesting diffraction information in the diffraction pattern. So this is a good segue to doing what we call virtual apertures. So if we want to have a virtual STEM image, just right click on the diffraction pattern and you can choose an ROI tool. So let's go with not an annotation tool, sorry, ROI. And oval, let's do oval. And I'm holding down a shift key so that that's constrained to be circular. Just going to put that over this diffraction disk for now. Go up to the spectrum image menu. And there's a nice option that says map signal dynamic. So it's important that we use this signal dynamic. And then what you get there is a virtual STEM image that's formed from that kind of virtual aperture that I just placed there. Now, this is a dynamic image. So that means that this will get recalculated if I make any changes to this little purple circle that I've drawn there. So if I go over here, that's forming a virtual dark field image with that diffraction disk instead of that one. Okay, same with this one. And then you see like loads of interesting contrast happening over here. So different areas light up corresponding to, you know, where this is strong intensity or weak intensity. So the area that's kind of interesting with this sample is actually there's a little group of particles down here. So so you've got one where we have a nice strong diffraction disk there, one there, and then one there. Right. So if we just very quickly grab some images from these guys, so we can have this one. So a neat way to work here, right? If you just leave this live. And then what do we do? So if we want to like grab copies of these, it's very straightforward. We just Control-C to copy that image, and then I press Control-Alt-V, and it pastes that map or that virtual STEM image into a new window for me. So I have that one is there. With this particular data set, I also like to do the same with the diffraction as I get a map of like where I am in diffraction space. So I'm copying and pasting the diffraction pattern. I've got my diffraction pattern, so I'm going to put that there. So I know that this image here corresponds to this integrated diffraction disk there. Go back to our 4D STEM data set, and let's just try that one. Okay, so do the same thing again, Control-C, Control-V, and we have another one, and then we have another diffraction pattern, right? So 2 diffraction patterns. Now we go for a third one. Let's try this one. So virtual image 3. And then we have the diffraction pattern 3. Okay. Right. So I very quickly just grabbed 3 virtual aperture images, and I've just kept the diffraction patterns there as a sort of a record of where I was. What do I want to do next? So this is still live. This takes up quite a lot of the workspace. So what would be nice would be to maybe tidy that up into a composite like we did with the EELS map. So that's something that's super easy. So we just do exactly the same thing. Now, I'm going to do this like in a very specific way. So I'm going to click this one, and this one, add, and then I'm going to click through this list in the same order. So, because they all have the same name, I've been a bit lazy and haven't named them. All right. So that's my RGB composite image. And that's helpful, right, for me. If I do exactly the same thing with my diffraction patterns, top, middle, bottom, add, top, middle, bottom. Now, like this works really nicely with this example because the only like the diffraction disks that are strong in these, basically there's only like one diffraction disk other than the 0 disk that's strong in each of these diffraction patterns. So they overlay like really nicely. So you can see which is the blue, which is the green, which is the red. Which, if I want to be kind of constrained with what I have on the workspace, that's actually pretty nice. So I have this nice composite there. And then I can just use this almost as like a key to like what color corresponds to what diffraction disk. So that's kind of a nice way with this data set to do that. I mean, some diffraction patterns, you'll end up with something that doesn't look quite as separated as this. If that's the case, I would probably prefer to have like colored circles and overlay, you know, just draw an annotation around the diffraction disk is another way to do that. And then it also, if you're kind of being more rigorous, it makes sense to actually name and like index things as you go along. So up to you, but there's various different ways that you can do that. Okay, so where are we going with this? So the what's very clear in the diffraction data is that you've got like these 3 particles that like really jump out like quite strongly. So the edges of it very, very sharp. So I can zoom in. Can I zoom in? Yeah, with the mouse wheel, use the hand tool and pan across there. So it's very obvious like where the edges of these particles are. If I look at the elemental map, yeah, I mean, there's some regions that are like gadolinium rich, but it's not quite as clear in the map by itself where the edge of the particle might lie. Now, one thing that I skipped over earlier when I just kind of launched into the diffraction extraction is remember, like, these are all linked, okay? So EELS and the EELS low loss and high loss was required at the same time. So obviously they're linked, but like this is acquired after the EELS, but because we have the spatial drift correction, like these have good spatial correlation and the data set is the exact same size in terms of like X and Y. So this picker is linked, right? So to all of these. So I can move my picker tool around in my 40STEM data set and it also like kind of tracks where we are in the EELS data set. And that's true of any data that's derived from any of these. So we can go and do the same thing with our, this composite diffraction map that I just pulled out. So I'm able to drag that picker onto this guy here, and I can then be like very confident that I can select a picker region that is maximizing the number of pixels that I want to stum from this particle here, right? So if we, okay, I'm a little lost with that. So I might actually start a new picker tool, or is it this one? Yeah, right. So it's actually, I kind of now want the high loss data. So let's just tidy up a bit. So I don't want that one. I think it's this one, right? So does it move? Yeah. So we want picker 1 from EELS high loss. Okay, so that enables us to just be like confident that we have most number of pixels that we can possibly get from that picker. So generally you want to always maximize your signal to noise ratio, and with the counting detector you can either do that like at the time by having a longer exposure time, like more passes if we're doing multiple passes. But the thing that we do once we already have the data is we usually sum as many pixels as we can spatially to like boost up our SNR, and we're trading some spatial resolution. In this data set, this is like particularly important because if you look at, so we look at this diffraction pattern, what we're looking at, we have a like really tiny convergence angle here. We set the microscope up in a regime that really favored the diffraction. We wanted to have non-overlapping disks in the diffraction pattern to aid interpretation. Now this is a condition that's really like not so favorable for EELS. So this convergence angle is like super small for EELS. So if we go down to a single pixel, you can see that the SNR in the high loss spectrum here, just for a single pixel, is basically heavily compromised because we're in a really diffraction favoring condition. But because we can sum pixels in the counting detector without any penalty, you can kind of get around that by just summing spatially, and then you still kind of have enough signal quality, like with trading off that spatial resolution. Okay, so we've got this pixel here, or this group of pixels. We want to be really, there's a couple more things that are kind of fun to do. So one thing that is kind of useful that not so many people are aware of, you can actually get information from like irregular shaped areas. So if you right click and we go to the ROI tool, so use a loop tool. And then, whoops, I drew that in a bit of a bad place. So basically you could draw around the edge of this. And then if you're really picky about where you are, perhaps that's better because we're then only in the screen area. I can Control C and I can copy that ROI. I can paste it onto the high loss spectrum image or the low loss spectrum image. I'm just going to do the high loss for now. If I have this selected, go to SI, sum in selected regions, then basically that's going to sum all of the pixels enclosed by that little loop that I just drew. So if you want to do something that's in the regular area, that'd be the way to do it. Okay, so what else do I want to show? I have like one more thing I think that I want to show with this data set, and that is the MSA tool. So PCA or denoising. Where does that live? Okay, so PCA is not in the analytical technique. So just remember that that is actually in a different technique, which is data fit. So you can go to data fit and you've got this tool that says MSA analysis. So you've got three buttons there. Simple denoise, PCA decompose, and Vinayak. So I'm not really going to go into this in depth. So PCA decomposition is going to give you the full PCA result. Vinayak is kind of an extension of that forces the components to be non-negative after the PCA decomposition, so it's more interpretable. Simple denoise just does the decomposition and then it reconstructs with the components that we choose. So it's just, as it says, simple denoise. And that's really what I wanted to do with this data. So I'm just going to do that now. So all I need to do is pick the high loss data and I press simple denoise. The software does some calculation. And what it throws me is this, what we call a scree plot. So this is like the eigenvalues of the principal component in the PCA decomposition. And essentially, what we're generally interested in is this like knee or like this inflection point. So where this becomes linear, we expect the data to just be noised. And generally, like when you do this kind of decomposition on counted data, so data from K3, like K2 or Stellar, because we don't have readout noise, we just have Poisson noise, the statistics in the data is quite well behaved, and it responds to the PCA treatment like pretty well. So we could, if I wanted to be like really kind of reduce the components to an absolute minimum, I could probably go with like 4 or 5. Might be a little bit conservative and just keep some. We can see that, like, you know, PCA has some assumptions. It's saying that the data is like a linear combination of components. And with this data, like this is like non-uniform in thickness. So if the thickness is varying heavily, that's definitely a non-linear effect. So if I have too few components, it's going to do weird stuff where the thickness changes. So I'm going to just arbitrarily, let's just go with 15. That's what I chose last time. Hit OK. We have like one final data set. I'm going to then use a picker tool again on this guy. So we're going to pick a new picker tool here because I'm getting a little lost in picker tools. So picker ROI2. So this is the denoise data. Let's clean that up. Right click, clean spectrum. And yeah, okay. So one thing that the reason that I've done this, okay, so right, we know that we don't have like the most optimal signal to noise ratio in the high loss data because we have this low convergence angle. So the denoise is going to help if we want to look at a smaller number of pixels. But remember, like PCA is like a reconstruction technique. So this is like no longer like really like real EELS data. So you have to treat it with a little bit of caution. So it's nice to look at this data alongside the original EELS data. Super easy. Again, all this data is linked. We just drag the picker from either the EELS high loss into the PCA data or vice versa. So I drag my picker into my original data. I have two pickers. Now, something that's pretty nice, if you right click, you've got this one that says overlay picker data right at the top. And I've got a bunch of options. I want to overlay it on the same picker object. So number 2, hit OK. And then we end up with just a single display, right, of the two linked picker objects at the same time. So if I basically have a huge picker region, these two data sets look exactly the same, or close to the same. And yeah, so we have like really high SNR in the raw data if we sum a lot of pixels. If we go down to a smaller number of pixels, so you see like the SNR in the raw data, which is the red one, starts to drop off. Because these are linked, it tracks really nicely because we're basically it's kind of like self-normalizing almost, because we're summing the same number of pixels from the same area. So it really helps you just sort of guide your eye with the fine structure in the raw data versus what you see in the PCA data. And this is like kind of quite a nice way to like rapidly look at the data. Because the PCA is kind of smooth and clean looking, but you know, we risk having some nonlinear artifacts, and the fact that we have the raw spectral data there overlaid with it kind of avoids kind of pitfalls, I would say, like if you kind of making mistakes with the data. And then yeah, as we kind of touched on earlier, all the data is linked. So if we want to have the same thing with the diffraction pattern, we're all good. So yeah, I think that's it's like a very like rapid like overview of how to work with, you know, just some of the kind of the very quick ways of looking at the data like this. But I think that the real trick here is that we make sure that the data is all the same size in the same area, and you could really only do this reliably because we're able to do the data acquisition on the same, you know, in the same session, same microscope. It's, you know, I think it's legitimate to acquire a spectrum image and then acquire another spectrum image like seconds later, but I would question doing the same thing if we took the sample out of the microscope and put it back another day. It would be pretty hard to find the exact same. I mean, maybe you might, if you were perseverant, you might have some success, but it's much easier if you can do it as a part of a single experiment. And then all of this linkage makes it like super fast and easy to work with. So with this particular example, it's just some simple chemical analysis, virtual aperture imaging, but you could do this differently. So we could have something where the 4D stem was set up more for like DPC, and we could have like a low loss like EELS spectrum image and do like kind of low loss analysis. So anything that you can do in EELS and 4D stem, you could effectively pair together with this kind of acquisition and analysis approach. And then, as I showed, yeah, so you can do it manually. It's very straightforward. You just hit the button yourself. Or if you want to do something more advanced, like the heating experiment or an in situ experiment, like I showed in the lecture, you can do this programmatically and get like a very large amount of data in an automated fashion. So
Yeah, that's great. That's great, Liam. It's probably a perfect spot to segue into the final session on the microscope. With Andrew with the in-situ data.
perfect.
Did have a question though. This data doesn't have any EDS with it, does it? But if you did have EDS, you could do the exact same linkage and.
Yeah, it would be exactly the same. Yeah, we just for reasons I can't remember, we didn't get EDS at the time. But if we did, we would just have one extra spectrum image, or even two, because we got 40 STEM and EELS, and it would behave in the same way. So all the linkage would be just the same. And yeah, it's a good question.
Perfect. And the diffraction, you're doing virtual apertures here with small circular apertures. But there's also annular apertures and any number of different types of data. Just wanted to, or apertures. Just want to point that out. And you can use the DPC tools to do quadrants and things like that.
Yeah.
So yeah, they're in the
Mask
there
tool,
was ones
right?
there, the mask tools. Yeah, so the bandpass and all that kind of stuff.
Oops.
They give you a lot of different options to.
Yeah, so that would be like a ADF, like a HADF, I guess, or you could do an ADF or something.
Yeah. Okay. Well, great. So Andrew, are you good to go on the microscope now?
Yep. I have
All right.
everything set up, ready
hang
to
on,
go
wait a
for
minute.
the
There was
in-situ experiment.
There was a quick
Perfect.
question here about the undiffracted beam. Is there a way to center the undiffracted beam and then create? Oh, virtual. Oh, yeah, that's exactly. Yeah. So yeah, that was just what we were talking about. So I guess I was thinking that question. I wasn't the only person thinking that question. Okay. Yeah.
Yeah, so one thing that I didn't show actually, if there's any drift, you can do a line SI by peak on these ones as well. So you draw an ROI. Let me just get rid of the mask, it's confusing. So you can draw an ROI over the bright field disk.
Mm-hmm.
And then if you go to SI, align SI by peak, it will go through and it will do like cross correlation based kind of drift correction, I'll call it, through the 40 STEM data set. Similarly to EELS, but just be aware when you do this with diffraction data, it's a bit more intense on the processing because the data is bigger. So it just takes a little bit longer, but it will it does allow you to do it, which is useful, especially if you have like D-scan artifacts. Let me see if we had any or not. So if I draw some marker through that. Yeah,
I think that's already
I think we might have I think we may have already corrected this data based on how much that isn't moving. Yeah, but if this was like moving around, you just follow the same logic. You draw an ROI that encloses the diffraction disk, the zero disk through like the full kind of range of the spectrum image. Align SI by peak, and it will generate you a corrected data set, which is useful.
Yeah, and also the definition of the center of the diffraction pattern is done. There's a diffpack tool for defining the center of the diffraction pattern because it usually isn't exactly in the right spot. But
exactly, yeah. I used that, but I didn't actually tell you. So it's this one that says assign center.
Yeah. And
the way it works actually is you're supposed to do two centrosymmetric spots around the center. So if I was to draw like there and there, you get this little square that is, I drew it slightly badly, but that's how it works. And then any of the masks, all of these masks will be centered on that diffraction center there. So if you don't assign that, the default will be the center of the image. So it's important to do that first if you want to use the mask tools essentially, or the DPC stuff.
All right, great.
Cool.
Excellent. That's a great data set. I really like that. That was 80 kV, 60, no, 60 kV, right?
This is 60, yeah.
60, yeah. Okay.
I think
Yeah,
so.
really, hybrid pixels really work well at low kVs like that. All right. So let's jump back over to the microscope then.
All right, I'll start sharing my screen. All right, everybody, we can see that. Okay, so we switched the BTFO multi-layer film for a dense wildfire heating chip holder, and so we have the wildfire holder control integrated into digital micrograph. So I'm still in the SAM-SI technique manager tool, but we switched from normal acquisition to in-situ acquisition. And so when we do that, it'll enable this wildfire tool palette so that we can control the target temperature, ramp time, if there's any recipes that we wanted to create beforehand to set up or to run a heating experiment, we could load those through this tool palette here. And then when we've turned on the wildfire holder through digital micrograph, down here on the bottom right, on the microscope control diagram, the microscope system diagram, it'll go from that the copper grid default specimen diagram to the DENS spiral diagram here. And then when we switch from normal to in situ mode in digital micrograph, so this is digital micrograph 3.6. Now in our SI acquisition, we have two options to acquire data. We have the capture, which would give us the normal multipath spectrum imaging, or we can actually do record. So what record does is it'll still do the multipath, but instead of adding each pass onto one another, it actually saves it individually. And then with our in situ package, we can go through post-acquisition and we can actually navigate through the different passes or the different slices, and we can see how the spectra or the spectrum image is changed with respect to time or temperature. And all of that will be linked through the wildfire holder and digital micrograph, so we can see, okay, at this pass we were at, I don't know, 300 degrees Celsius, and then at this pass we were 500 degrees Celsius, and we can see, you know, how the chemistry changes with time and with temperature. Okay, so while Liam was giving his tutorial, I found a cluster of, so these are iron oxides, so Fe2O3, that have a hydroxide phase. They're hydrated, and so the experiment that we're going to do is we're gonna concentrate on this cluster of Fe2O3 particles, and we're going to try and see how or what the kinetics of reduction are. So we're going to heat this up in a vacuum environment, and then as we heat the nanoparticles up, they should start reducing. So the oxidation state is going to change from an Fe3+ to an Fe2+. And then we're going to monitor that change not only through the ADF image, but through EDS and through EELS. So the nice thing about EELS is that we can look at the near edge fine structure of the L2-3 edge of iron, and we can monitor how that fine structure changes, and then that'll tell us how the oxidation state or the projected unoccupied density states are changing as a function of temperature and time. Okay, so let's get started. I'm going to go and I'm going to make sure that we're still in the same area here. So we just inserted the holder, so there's going to be a little bit of drift. On the left-hand side here, we have the silicon nitride membrane, and then towards the upper right corner here, we have the vacuum, and then there's a thinner part of the membrane, which is kind of like the lighter gray area there that the nanoparticles are sitting above. So I went and focused the image there, I'm going to go ahead and click preview. And then I'm going to set up our spectrum image so that we have everything in the field of view. Let's see. So I'm going to keep, so we'll keep a pixel dwell time relatively fast. I increased the probe current a little bit, so the spot size number was decreased. That way we just have a lot more probe current, so we get more signal in the spectra per pass. I'm going to keep our pixel time to be 2 milliseconds. And then we'll do a pixel array of about 45 by 45 pixels. So that gives us a step size of about 7 nanometers. We'll have subscan on, so we'll have the spatial resolution in the ADF image to see any detail that's changing in the particles. And then that we'll sacrifice a little bit in terms of spatial resolution in the spectrum image, but we'll still be sampling sufficiently high enough that we can monitor changes that are occurring locally in the particles. Okay, so I'll set up my spectrum image there. And then once we do that, I'll go ahead and start recording. So we're going to start acquiring the SI before we start any heating. That way we kind of have an idea of what's going on in the image. I'm going to kind of decluster a lot of this. And then I'm going to monitor changes in the spectra there. And then over here. So we'll keep these live. I'm going to kind of reduce these guys here. So we'll see, we have morphology and then we have chemistry. Okay. And then what I'll do is I will, so we're going to monitor how or the behavior of the reduction of the particles. So I want to do elemental quantification. So I'm going to, like I was describing in the previous, in the first live tutorial that we did, we can upload recipes. So I'm going to go ahead and I'm going to load. We have a pre-set recipe for Fe2O3 experiment. So it's going to look at the iron and the oxygen edges there. And then we're going to go ahead and we'll say quant. So that's going to give us these results down here. Okay. So a little bit of a shift there. Edges. Let's see here. So we mostly have iron. Let me change. Let me change this a little bit so we just have the iron. There we go. Make sure. So that way. Okay, so now we have the Fe2 and the Fe3 plus. So now when we map the two different elements, we can monitor how. So we have a so Liam already had extracted standards from an Fe3 plus sample and a known Fe3 plus sample and a known Fe2 plus sample oxidation states, and he extracted external standards and then loaded that into the recipe. So now we can monitor how this portion of the pie basically changes as a function of temperature. And we can do that live. And then we also have the ADF image here. Get rid of the survey image, or the originals image there, so that we can look and see, we can see how the morphology of the structure changes. Okay, so really the kinetics of the reduction really doesn't start accelerating until much higher temperatures. So to save us a little bit of time, I'm actually we'll start, let's see, we'll do 100-second ramp time and we'll ramp up to 400 C. So I'll go ahead and click ramp. And then I will monitor So as that, we can see the change in the temperature right here, and we can see the update in the ADF image. So this will allow us to monitor how out of focus. So the membrane will warp or expand and contract or expand a little bit as it's heated. So that the sample itself is going to change in the Z direction. So this will allow us to kind of monitor the changes in the ADF image as we go. And
Andrew, just a question. Do you have the drift on?
Yeah, I just noticed that I don't. So I'm going to go ahead and I'm going to pause this. I'm going to stop record. That was a very critical thing. So the nice thing about having, oh, yeah, I didn't like that. Okay. So the nice thing about having, let's trying to do all that. The nice thing about having drift correction is that we can monitor the drift as we're doing the in-situ experiment. So that's a very important aspect that I forgot. So we'll have continuous going. I will. Okay, so I'll reset that up. So this will be our pre-drift area there. Kind of reduce the area. We don't really care about the membrane itself. Kind of. Okay, so this will help keep track of that. So I'll go ahead and, so we have drift selected now. So now it'll monitor and adjust the scan as the drift occurs. So I'm gonna go ahead and click record. Okay, so it's gonna do our pre-SI acquisition measurements. I'll reduce that. I want to monitor the fine structure as it changes. Okay. The spectra on the EDS, how that changes. Reduce these guys. And then I'll have our live spectra going. Get rid of these guys. Our live EDF image. We can kind of see how our spatial drift is going. Oops. Okay, so I'll go ahead and reapply our recipe here. And then we'll do live quants. All right. Okay. So we have that going. We're monitoring spatial drift as we go. All right. So I'm going to go ahead and I will collapse that. I'll go back to the wild file folder because we want to resume. So I'll go ahead and resume again. So now we paused at 180. Now we're going to go back, continue our ramp up to 400 degrees Celsius. So the nice thing about doing the fast acquisition, so we have a very low, or we have a very fast dwell time. So it allows us to monitor the spatial drift between each pass as we're doing the in situ spectrum imaging, and allows us to correct the drift on the fly, basically. All right. We're kind of slowly approaching 400 degrees Celsius there. We're monitoring how the iron is reducing. So we're still majority Fe3+, but we are getting a little bit of 2+ there. And then we can see how the fine structure is changing in the spectra. So that's nice. Okay, so we've hit 400 degrees Celsius. Now we can start our slower ramp. So we'll go up to 850 degrees Celsius. We'll do a ramp time of roughly 900 seconds. So we'll do it slowly. And then we'll go ahead and start our ramp. And then we also have the EDS data too. So that's kind of nice because it helps kind of confirm what we're seeing in the EELS data as well. So we should start seeing maybe some morphology changes. We'll start seeing maybe some holes form in the particles, especially the thinner ones initially. And then as we go higher in temperature, what we've seen in the past was we start seeing some consolidation of the particles. So as the particles go from more of a 3+ state to a 2+ state, as it's being reduced, we start seeing the kind of the consolidation or the like a sintering of the particles into larger conglomerates. And then right here, so we're measuring the drift, and we can see the number of measurements as we go. So we can see what the spatial drift is. And then I'll go ahead and make sure that we're in focus. I think typically in the past, we've seen about a 8-micron shift in the Z position as we increase in temperature. And so we're keeping the ramp time slow enough that we can, monitor the changes in the ADF image, so we can see how the focus is changing, so that this always stays in focus, and then we can slowly see how the chemistry is changing. So if this is too fast, then we get changes mid-scan, and so we might miss something in the spectrum image, and so we want to make sure that the timing between the scan or the refresh rate of the spectrum image is in sync with the ramp rate of the holder itself. So now we can start seeing the holes grow a little bit bigger. And you can you'll see some kind of fluctuations here. So it'll kind of go back and forth, but then over time, the overall portion of the pie should start becoming more green than it is blue. Let's see, so we're still 490, we're approaching 500. Yep, so now we can start seeing larger holes in the spectrum or in the ADF image. A lot of focus there. You can start seeing some maybe like core shell particles form there. Maybe we got some Kirkendall voids forming. Where we're at, still at almost 530.
Well, Andrew, the data is getting streamed to disk, right?
That's correct. Yeah. So as we're not saving this in the free memory. So this is as we're going after each pass, it's saved to a file that's continually being rewritten or written.
Okay, and that also has the temperature plot along with it.
Correct. So there's a separate, there'll be a separate, so it's saved as a raw file, and then there's a separate DENS or heating holder file that saves the temperature and time data, and then that's linked with tags to the spectrum image data. So then, if you open the data set as an in situ data set in digital micrograph, you can navigate through time, temperature, and then that will update the spectrum image. So as you navigate through the slices, then yeah. So that's really nice, because sometimes, I mean, this data set will probably be on the order of, 20 to 50 gigabyte, probably 50 gigabytes with the low loss, the high loss, and the EDS data. And so that's nice because you're not holding all of that data in the memory. You're just looking at, and then it'll be nice for post-processing as well, because when you open the in situ data set, you're not opening the whole 50 gigabytes, you're only opening the every slice.
Okay, so it's just moving in and out of the disk and memory and back and forth.
Right.
Yeah.
So yeah, although like a single pass of EELS is not a single multi-pass spectrum image is not super high, on the order of maybe a gigabyte or a few gigabytes at most. Because we're saving each pass individually, the data sets can be a little bit larger. But because we stream them to a raw file, we just access the data as we access individual slices, and we don't access the thing at once, all at one time.
Got it.
And then the other thing, you can also, so we're doing drift correction now, but if there's a little bit of drift between frames, we can also, so in the post data acquisition, we can also apply a drift correction there as well. So if the data set's not quite lined up between frames, we can also readjust for that. And then if we find out there's not a lot of changes between frames, we can always add frames together so we can increase the signal to noise. So if it doesn't, if there's not a lot of change in chemistry between, I don't know, 500 and 600C, we can add all those frames together. And then that's nice because that'll increase the signal to noise a little bit more. Go. We're seeing a little bit larger changes in the Z. A little bit out of focus there. You can start seeing that the voids get a little bit larger, and actually we start seeing the particles collapse. I also noticed too that in the composition readout here, we're getting a little bit more Fe2 plus than 3 plus. So this was kind of sitting around a few percent. Now it's the Fe2 plus is now 11% compared to what it was before. So now we're starting to see a little bit more. The Z drift is going a little bit faster now, so I got to pay attention a little bit more to the focus as we're going. And then up in the spectrum image, you can see, so there's the blue curve, and then there's the orange curve. So the orange curve is actually this is the MLS fitting weighting, what portion of the standard makes up the experimental data set. So we can see here that the Fe3 plus is still the more dominant phase, and so the blue spectra is higher in intensity than the orange standard. the orange part of the spectra. So we can also see visually what's happening on the fine structure there, which is kind of cool. So the MLS fitting is basically weighting, based off of the chi-squared value, what creates the best fit in terms of percentages. Yeah,
So most, yeah.
Go
I was
ahead,
gonna say, most EDS detectors would have been swamped by now with this high temperature sample, right?
Yeah. So that's one thing that I forgot to mention. So we're using an Elite T EDAX detector, EDS detector, and the detector is unique in that it has an IR filter. So as we heat a sample inside the microscope, it'll give off infrared radiation or even visible light if we go high enough, and that can actually swamp the background of the detector. So it can actually consume or make some of these peaks, the lower energy peaks, harder to see. And so we have a filter that actually will get rid of that IR background, so that we can actually view the EDS spectra during the heating experiments.
Yeah, it does cut down a little bit on the low energy sensitivity, or light element sensitivity, should I say?
Yeah.
But that's what having the EELS and the EDS together at these high temperatures is kind of unique.
Right. So now we can see the portion of the pie is getting a little bit higher with the Fe2 plus. It's kind of consistently getting higher. We're keeping the sample in the field of view, which is nice. So the drift correction is doing its job. And then we're about 100 degrees set off from kind of where our final set point is. But it's really manageable. So, the nice thing about the DENS chip is that you don't have a very large drift in thermal drift because of the way the chip's designed. And then the drift correction and digital micrograph really complements that in situ experiment because it keeps everything in the field of view. And then we can monitor live how things are changing. So now we know, with this quant results, this live quant results, we can kind of see, are we seeing what we expect in terms of changes in chemistry, which is the idea behind this experiment. So again, it kind of goes back to what we were seeing with the DPC, is that we can do the analysis on the fly. So we're not looking at the data post acquisition and saying, oh, well, it didn't really reduce, or we didn't go to a high enough temperature. And we're not just looking at morphology changes. We're looking at changes, other modalities to see, are we observing what we expected to see, and is the morphology changes corresponding to what we expect to see in the reduction reaction. And so this would also apply to if you were doing a biasing experiment, or if we wanted to do a liquid experiment. It might be a little bit harder with EELS, but we could do the same thing. The same concept would be applied through digital micrograph. And then if we wanted to, unfortunately, because of the way the optics work, we can't have a seabed pattern and a EELS pattern simultaneously because of the way the optics work and the spectrometer. But we could do the same experiment over again. So if we went back to the BTFO sample and we were able to mount that to a biasing chip, we could bias the sample and we could see maybe domain walls propagate, or we could acquire 40 STEM data sets of different biases, and we could see how that changed structurally, or how the domains propagate as a function of time or bias. So not only are we getting chemistry, but we're also getting the functional properties as well, and the structural properties. So we're about 20 C from our final holding temperature, or our set point. So we're we've actually, the ratio is flipped now. So now Fe2 plus is about 20 atomic percent of the sample that we have. So we've kind of kept it in this area here. Let me see if I will, yeah, so it's kind of drifted a little bit, but we'll go ahead back there. Yeah, so it's flipped. So now Fe2 plus kind of, it's about the same. So now it's neck and neck. And then if we were given more time, so now we're at 850 C, so we're at our final set point, right? So now focus that. And even with it being a little bit out of defocus, the drift correction is still able to kind of keep the sample in the same area. And even with morphology changes, there's enough that the sample is similar enough that we can still keep the sample or the desired area in the field of view. And we kind of slowly over time, we can see how this changes. And so at 850 C, the reduction reaction, the kinetics occur a little bit faster. We could make that go a little bit quicker. So let's see. So if we just kind of slowly ramp things up. So instead of doing a ramp, I'll just do a direct temperature. But I'm just going to do it through kind of a stepwise degree. So we'll go from 850 to 851. And then we can see kind of how the temperature changes. I can see how the focus changes. Do I need to adjust anything? We can see the portion of the pie is getting a little bit bigger now for the Fe2 plus. So now I went from 21% to roughly 24% in some areas. Then I'll go from 851 to 852. And we can see the temperature. We can monitor that, how it slowly goes up. So we can see our Fe2 plus getting a little bit higher. We'll go to 853. Now the ratio has definitely changed. So we're now going, now we're 25-15. So the ratio is definitely flipped now. You can see that the portion of the pie diagram has changed. The pie chart's changed. So now it's mostly or more Fe2 plus. Let's see, 54. And all I'm doing is I'm just typing in the desired target temperature and going. So it does like a really fast ramp rate. So we don't have to constantly change the ramp time.
And again, each one of those steps gets stored in with the data, right? So you can go back and see exactly when you bumped up the temperature and stuff.
Right. Yeah. So now we have all of this is linked. So as we're changing the temperature, we're linking that. The data set's linked to that. So what I'm doing is I'm just kind of letting it hold for a little bit in between each pass, so we can see, we have a few passes at each temperature. We can kind of see how it's changed as a function of temperature. So how the reduction reactions changed. We'll go maybe 857. So we'll do a little bit higher jump. So it's going a little bit faster now. Let's see if we went to 860. $870. They'll do a couple more passes just so we can kind of see, right? So it's not, the kinetics won't be instant. It takes a little bit of time to reduce. But as we go higher and higher, the kinetics should get faster and faster, right? So now we'll go to 870. We're just kind of slowly controlling the experiment. We'll jump a little bit higher. So we'll go to 890.
The suspense is killing me.
I know. So now we can see it's going faster. So the portion of the pie diagram is getting larger and larger. So the Fe3 plus is kind of slowly being kind of wedged out there, as you would say. And then we'll go to 900. So we'll stop at 900. Yeah, so now we're almost 30% of the Fe2 plus and 10% of the Fe3 plus. So we kind of slowly see it's getting slower and slower. We can actually start seeing that there's not really individual particles. It looks kind of like things are the particles are kind of consolidating there. We have we have like one large particle over here. Maybe the morphology is a little bit different. I'm sure if we let this go a little bit longer, you know, we'd probably get maybe some type of equilibrium shape, maybe some faceting would occur, or something like that, rather than having these kind of nice round surfaces. But we're also kind of doing it in a controlled manner because we don't want it running away. So we don't want something happen mid-frame and it just kind of, you know, particles go away or something happens, we can't capture it. So we can kind of slowly ramp things up. We can accelerate the reaction if we want to a little bit more. We can, if we see things are going a little bit slower, we can increase it, or if they're going too fast, we have the control of decreasing it a little bit there. So you can kind of see now we're at 30%. It's kind of slowly reducing there. Go. Nine, 10. Wonder if we can get it so that's just Fe2 plus. Now we're at 33% iron. Let's see, let's go 920. A bit of drift there. 32%. Then we can kind of see here how the fine structures changed as well. So now the model has changed the intensity or the weight of the fit of the Fe2 plus, which is an orange, versus the purple fit, which is the Fe3 plus. And then we can also kind of see how that changes here in the quant results. And then let's see, we'll stop it. Let's go to 950 and then we'll stop the experiment. We can kind of also see how things are going live. So we're only sampling one specific area, but as we go through, we can kind of see how things might change a little bit. Over here, let's see maybe what this particle looks like. So the oxidation state's different in different areas. So post acquisition, we should be able to go back and remap these out. We can kind of see, you know, maybe in this area we have more of the Fe2 plus, or maybe the kinetics happened, you know, progress differently for other areas. But this will just kind of give us an idea of the reaction that we are expecting is occurring You can kind of see them consolidate. Okay, so I think for the interest of time, so once we're done with the experiment, we can kind of slowly ramp things down. So if, you know, once we have everything done, we can just kind of set everything back to room temperature, or we can kind of slowly ramp things down. Let's see, so we'll go back to 25 degrees Celsius, and we can do that over, I don't know, maybe 60 seconds. So I'll go ahead and I'm going to re-ramp it off. And I'm going to stop the record. So now all the data is saved. Okay. And then we will, all the data in this. So we have our ramp times. And then I'll go back and keep that search there. So you can kind of see we've changed quite a bit there. Then we can go, you know, once it's cooled down, so we're still kind of at 300 degrees Celsius, but we kind of keep track of everything. And then, you know, because the drift is not too significant, now the data is already written, we can kind of keep track and maybe do some post and acquisition analysis. So maybe we want to get more kind of detailed maps, or we want to get a higher signal to noise. Maybe we wanted to do more, like maybe we need to do some atomic resolution imaging, or kind of want to see post-mortem what happened to the particles. And we kind of got before and after of the area, then that kind of do that at this point now. And now we have all of our data sets, so it writes it to the data set's written to a spectrum image. So it's already in the data, and then we can also save the workspace, but we can link all these together at once. Let's see, so we saved it in, we'll go back to Liam's folder. Go, and then I'll save this. So it already wrote the raw data. So this in-situ 11 has all of the raw files and the DM4 files. And then I'll go ahead and click save there. So it'll save the data. Then we can go through and we kind of see like how the slices have changed. That's kind of cool. Yeah. So that's pretty much it for the heating portion of the in situ experiment. So it's kind of recap. We have now in the newer version of the digital micrograph, we can do spectrum imaging. So we're not just limited to a specific area. Now we can take spectrum images as we increase temperature bias, or other stresses to the sample, and we can link those through the wild folder toolbox here, wild file folder toolbox here. So now we can look at, we have spectrum image data and temperature data as a function of time. And we can do all the data analysis within digital micrograph, so you don't have to export or import anything into digital micrograph. And everything's kind of controlled in one kind of area there. And then I don't know, Liam has done a lot of work with scripts as well, so you can kind of do custom setups. So you can, maybe the nice thing about this is integrating in with Python is now you can do very long. So this was a fairly quick experiment. It only took us less than an hour. But if you had something where you wanted to get a little bit more high fidelity, higher signal to noise, maybe you would pause for maybe 5 minutes, take a spectrum image, and then ramp the temperature up to a different set point, take a spectrum image for 5 minutes so your signal to noise gets higher. And that might take you 8 hours to do, depending on how large of a temperature range you wanted to go to. Now you can do all that automated through scripting, so you can kind of like set it and go, and then if you're doing heating experiments, maybe you have to be a little bit more present just so you can adjust the focus. But the automation will help a little bit in terms of keeping track of the data and coordinating everything for the acquisition, so you don't have to constantly be sitting there. Were there any questions that came in during the experiment?
No, actually, no questions.
But yeah, that's a good point about the scripting, Andrew. So I just expand on that a little, but because so what we're doing here is we've got the temperature is just it's like a ramp, right? So going very fast with the spectrum image is probably the best way, so that we're not like changing the data too much. But what you can do with the scripting is you can basically program it so that the holder will change at certain like points in time. And so the way that I've done that in the past is I like trigger like a holder change at the end of the spectrum image pass. I think that's what Andrew was describing. So what you would end up with is, instead of this like ramp in your we take the heating as the example, you wouldn't have like this ramp, you'd have a step. It would like be a plot that looks like stairs. So it basically changes, but only when you're not really acquiring data. And that kind of methodology is really nice if the spectrum image passes like take longer to acquire. So if you have like longer dwell time per pixel, or if you want like more pixels, that's a nice kind of alternative way to do the acquisition. But you can do either. So that having a ramp is the easiest because you don't have to do any scripting, but you can set up more complicated stimulus conditions with scripts, and we can do it like heating and biasing, and depends on the holder, but yeah, nice different ways to do it. But yeah, and then having these time series that are streamed to hard disk is really, really powerful, because then you can have like very, very large data sets, because you're only really constrained by space that you have on the RAID array, which is like multiple terabytes of data, rather than it having to fit in the system memory, which is usually a few hundred gigabytes. So it's yes, it's very, very powerful. Good. Yeah, that's a fun little experiment. Good demo. Like it.
Well, I guess if there aren't any questions, anything anybody would like to see specifically? But yeah, no, yeah, that kind of got across the things we wanted to talk about with the different detectors linking into the high-speed data acquisition, and then being able to use that acquisition and data analysis and yeah, and you know, generate great data.
Yeah, and the nice thing is everything's kind of incorporated into one system, so you don't have to, you're not having to convert file types or changing software. Everything's kind of linked together in one thing. So you get the data, you get your feedback, and then you can design the experiment or modify parameters as you go.
Yeah, definitely makes life easier.
Yeah. Yeah, what was it, Liam? Like the first couple experiments that you've done with the heating holder was like, you know, several hours, and then, you know, once kind of these were integrated, the time was cut down significantly, right?
Oh gosh, yeah. The first time I did like in situ spectrum image, it was more like a prototype method. So the data acquisition was, you didn't get like the time series in the same way, but mainly like none of the processing tools existed. So you couldn't do things like align SI by peak or map in like the time, you know, you can do EELS maps in the time domain. And like not having those tools meant, yeah, it took me, I think, I think I spent multiple weeks doing the first data set that I looked at, and it was only mapping copper. So it was oxidation state mapping. So there were three flavors there were three maps, one for 2+, one for 1, and one for 0. But only one ionization edge took weeks. And then that data set that I showed, the K3 data set right at the end of my presentation, that has more data. So like more slices in time by a factor of 2 at least. And like obviously at least 6, 7 ionization edges, and each of them like concurrent standard. So we're looking at like, you know, like say like 10, 12 maps. Like getting the maps out of that data, I think took like a day. So it's massive difference in like productivity. So yeah, you can kind of, yeah, previously it was, if you wanted to do like a big complicated experiment with lots of signals, it'd probably be impractical unless you wrote your own. It would definitely be impractical unless you had scripts or software tools to deal with it, because it just takes so long to go through the data when you have that many spectrum images.
Yeah.
So having the software tools as well as the acquisition kind of capability is it's really key. Yeah, because you can get like tons of data, but if you can't process it in a meaningful time, it's not super useful. Just takes up hard drive space, I guess, doesn't it?
Yeah.
Yeah, but it's definitely like a really great workflow. And yeah, I guess we didn't really show much processing, but in terms of if you're familiar with how to do any processing of EELS or spectrum imaging, it's basically an extension of that workflow that we already used. So generally, if you press any kind of EELS function on a time series, what it will do is it will ask if you just want to either you process what you can see on the screen, or it says, do you want to process the whole time series? And then it just generates you a time series from the data. So you'll have a series of maps or a series of NLS bits or such. It's a nice, yeah, it's easy and it works well. So I am a fan, an ambassador for the experimental workflow. Yeah.
Yeah.
Ray, Liam, and Andrew, thank you so much for the demo. Sorry, just popped in. This was really great. I actually had one last question about the reduction experiment on the iron. So, how have you looked at doing this experiment without the presence of the electron beam? Because the electron beam, of course, also has the potential to reduce iron as well.
That's a good question, actually. Do you mean in the electron microscope, or like as a different technique, or do you mean like getting an image at the beginning, heat it up, and then get one spectrum image at the end, or do you mean like no electron beam at all?
The middle option that you mentioned, yes. So
yeah, because that would be really easy to do, and it's definitely, it's not something that we have done, but it would be definitely worthwhile to investigate for sure. Yeah, I think you're right. I think when we did it last time, you can see with prolonged exposure that I think you get some FE2. You're right. So it's an experiment that should be done. That touches on a good point, actually. So you should always like consider like what's the beam specimen interaction, because it's all well and good like doing a nice experiment, but if you're actually inducing the change with the microscope, then is it representative? It's a good question. So there's some experiment. I tried to do a similar thing with silver oxide, and the silver oxide was super unstable under the beam. It turned to metal almost instantly. So we ended up just not doing that experiment. But there are like kind of approaches that you could adopt where if you know something's beam sensitive, that you'd probably have to design the experiment in a way that's more favorable for a low dose experiment. So either, I guess you could just do an EELS only experiment with a defocused probe. That would be much lower dose. And then you can also decrease like the probe current. You could have like coarser step sizes, but it's definitely not something to ignore. And that you've given me that. I want to do that experiment now. That's a great suggestion.
Yeah, well, thank you again. I think there were enough questions today, so I don't have anything further to say. Thank you so much for the live demo. This was a great addition. Thanks all for attending that are still there.
Yeah. Yeah, thanks for arranging it. And again, I'd say the same, like thanks for everyone for signing up and attending. It's been like fun to present and demonstrate the software and the hardware capability and see all of the great talks in the morning session as well.
Yeah, thanks for your attention, everybody. Thanks for joining.